Thank you. Just a small technical check-in. Thanks very much, folks. And yeah, the title here, blimey, we're gonna mix it up a bit because, as Rakesh said, we're kind of like past the point where it's pure research to make a HMD for mixed reality. There's at least two generations of Meta Quest from Quest 1, 2, and Pro with pass-through, and of course we've just seen the release of the Apple Vision Pro also for mixed reality. So I'm going to sort of like bring us back and sort of like tether us to the history of what this really might stand for in the space of computing and interfaces, and also introduce some problems that really are the next decade's problems that are definitely not in the products yet. Okay, so I'll start with a quote. I wonder who knows where this quote is from. It was at a time when somebody standing actually in a live demo, not just a presentation, said, if you were supplied with a computer that worked all day long and was instantly responsive to every action you had, how much value could you derive from that? Now, hands up, who knows what that is a quote from? Anybody? Okay, this is going to be good. I'm going to join these communities hopefully together a little bit. That was from Doug Engelbach in 1968 at what was called the mother of all demos. Now, the mother of all demos, if you don't know, is where he introduced the graphical user interface, the mouse, some spreadsheeting, networked computers. And remember, this is in a time before PCs, before actually pretty much anything. It kind of started with the Auto, which was sort of like the precursor of a lot of what we have today in terms of those graphical user interfaces and how you interact with computers, with mice and now touchscreens and so on. They're all precursors of that the mother of all demos. And, interestingly, that generation of PCs ultimately landed in this mobile form factor that's in your pocket. And it really is, good enough that we can answer the question, what value is? The answer is, I don't know, billions, trillions of dollars. It's the biggest companies on the planet are trillion-dollar companies, and that's the business they do. And they do it because it's useful to human beings on the planet for many reasons. And now there's virtual and mixed reality. So where's this fitting in this kind of trajectory? What is the story here? What is it beyond those PCs and the mobile phones in your pocket that actually is being enabled with these VR and MR devices? Well, I'll leave it at this. A lot of progress is being made within the product spaces, and the fact that two very big companies are investing heavily should give everyone very good confidence that this is a new generation, whether it's for productivity or gaming, both, and that those things really have their legacy in those PCs and the mobile phones. Now, it's not necessarily going to completely replace those things, but certainly it's extending them in the same way that certainly the PC extended the precursors and mobile extended PCs and didn't necessarily replace them. Now, I think a lot of people at this workshop are going to be here to talk about essentially the great work that's been done on essentially building those mixed reality displays that you can think of as rendering surfaces that go beyond just a 2D screen. So for that, you need a lot of technology from computer vision. You need the SLAM systems, hand tracking, eye tracking, body tracking, object reconstruction and scene reconstruction, scene understanding. A lot of the classic problems in computer vision need to be solved. And then you get to have these incredible 3D visual displays, these auditory displays, spatialized audio, and even haptic rendering devices can start to interact with a mixed reality of the physical world that passes through, but also the actual objects that are completely virtual being rendered into, both visual, auditory, as well as haptic modalities. But I'm going to put it to you that if we think back to sort of like Doug's original point, then there's something missing from this picture. So it's amazing and we're on a great path and products are being built, but something's missing from what it could ultimately be. So he was saying, what about a computer that worked all day long and that was instantly responsive to every action that you have? Now, I don't know how obvious it is, given the excitement that we've got from the different companies producing the mixed reality devices that are these sort of new rendering surfaces. But, for something to work all day long, it has to work everywhere I go. And, I can't put those big headsets on my head and walk around. I can't be in a car driving with them. I can't certainly be on my bike, which is a great hobby of mine. I can't do a lot of things in those wearable computers. I can certainly do a lot more than I could with the desktop PC and even with the phone, but it can't be with me everywhere because the form factor is wrong. And for it to really be responsive to every action, it's interesting to think about what an action is. Is an action something that I did right now, because I clicked a mouse button or tapped a screen, or is an action a sequence that might last, minutes or days or even years long, and it's my progress through life as I try and get fit on my bike? And you can't immediately see it. It's sort of something you have to infer over sort of like a long distribution, a longitudinal capture of your life. So there's something missing there. And the other thing to think about is, what else is here that isn't connected yet in that story of immersive wearable 3D displays? And it's, well, now AI is here. So this is very exciting. How on earth are we going to collide these worlds of the beautiful mixed reality, immersive 3D audio haptic visual displays and this amazing AI? And, I claim that basically that is exactly what we've got to do, to bring the value to a completely wearable computer that's responsive to all of your actions over all time, so that you can derive the ultimate value in your life, and society can derive it over many generations, as has happened with computers. We're going to have to combine wearable computing and effectively these mixed reality technologies with AI. And how are we going to do that? That's really what I'm going to talk about. So hopefully we're going to see a new set of problems here that are not necessarily in everybody's labs, but that start to make their way there, as we see that some of the other problems of mixed reality are really being solved quite nicely in the products now. So, okay, so AI is here, but there is a gap in AI. So hopefully everyone here has had some good interactions with ChatGPT and all of that, right? Who has used ChatGPT? That's great. That's a win for OpenAI right there. That's 100%. And who wishes that ChatGPT didn't require you to type in absolutely everything every single time you wanted to know something about you, so it can now help you with your problem? I.e., if only it could have your context, right? So, so it's about 50%. Some people are skeptical, some people are scared. Okay, so what I'm going to say is that basically the real problem is not AI. That's kind of been done to a level that you can have a conversation with a computer now. It's contextualized AI, and it's contextualized AI which can be solved with wearable computing, with sensors and things basically that connect context from your physical life to that kind of AI. And that comprises the context, which comes from an all-day wearable set of signals produced by machine perception. It connects to your digital reality, not just your physical reality. So, you've got all that beautiful context that you have from your interactions on WhatsApp and Instagram and your emails, etc. But physical plus digital is context. And then, it's connected to that AI in various different safe ways. And basically, that's where all the reasoning and other forms of prediction come in. And that's very powerful today. We know that. But the two things are completely separate. Today, all of that context for physical reality is only available in devices like those Quest Pros and that new generation from Apple. That's where devices actually do understand you, your hands, where you're looking, what's in your environment, etc. But they do it in this form factor that you can't wear everywhere. And then there's the AI that seems to, be readily available ever more, from various big companies. And we've got to combine the two. So this is the always on AI challenge. It's not AI that you go to a computer and type. Two, it's AI that basically understands your context all of the time, not just through a short moment, but basically through weeks, months, and years. And that's the gap that we need to close for a truly compelling second wave of human-oriented computing that extends past where mobile phones have got today. So to begin, I'm going to basically motivate the idea of what would it take for machine perception and our computer vision that powers that to essentially provide signals for a day in a life. So I'm a glasses wearer. When I wake up, I kind of reach for my glasses. I put them on, and from that point on, I wear my glasses until I take them off. Now, that's because they add incredible value throughout my day. They let me see properly. And that's true for a lot of people. And a lot of people who don't wear glasses have had eye correction. So it's actually true for quite a lot of people. These glasses or other wearables are going to have to capture signals throughout this day. Now, realistically, there are situations when I don't want my devices to be with me. And then there's lots of other places where I need these devices to be with me and I need them to capture signals. And the granularity that they need to capture is much finer than I think people have understood for the current sort of generation of computer vision algorithms when we think about hand tracking and reconstruction and so on. So we need signals that go beyond essentially sort of like a moment's interaction or one experience that captures the entire breadth of life. And I claim that to do that, basically to enable this, what we can think of as a lifelong, always on AI, we're going to have to solve the context gap. That's going to require us to solve new wearable machine perception. That's going to require us to look very, very seriously at a new generation of algorithms that work with incredibly low power and with sensors that are much worse than what you're used to currently, much worse than those even going into our current products, that the big mixed reality ones where there's lots of form factor and real estate for sensors and compute. And ultimately, I'm going to claim that actually maybe we're going to have to look at this entirely new class of computer vision and machine perception, which is a distributed computer vision and machine perception solution space. And I'm only going to touch on that to kind of motivate people here who might be just thinking of a single device and single algorithms running on that device to solve computer vision. We're going to think about instead a distributed machine perception set of algorithms that really have not been looked at yet. Okay, these are the challenges of the next decade in CV and MP. I think it's very exciting if you're a new PhD in this area. There's lots of things to do here. Okay, let's get started. Wearable machine perception. So we got to the Quest Pro. It's good. It does a lot of things, a lot of computer visions in there. If you haven't tried one, try one soon. But we need to get to the glasses on the other side of the screen, because otherwise I cannot wear it all day long. It cannot be with me in the places I need that context to be. So that's where we introduce Project Aria. So Project Aria, which you can go to projectaria.com if you're interested in anything I say, sign up, get a device, play with it, bring it to your lab. Essentially is our move into a class of glasses form factor system that has the sensors that we expect for future generations of AR glasses and also augmented intelligence glasses, so AI glasses that are there to help you. Now, the difference is that these glasses really allow you to start to get context from the egocentric perspective. So we've got data sets that we've been building with partners in universities that are really very novel. They include not just this egocentric RGB view that I'm showing you from this like breadth of people's sort of everyday activities, but also eye tracking, so where they're looking, hand pose, what they're interacting with, information about the scene through spatial and temporal frames of reference that are consistent, that are delivered from the SLAM systems. And it allows multiple devices to be in sort of like a shared coordinate frame and share information over time as well. So Project Aria is a push towards, number one, make a system that is wearable. And then two, let's start to look at the signals that are what we call ecologically valid. So this is data from real people's lives, really where they are, really interacting in sort of non-trivial spaces. The hardware itself is really a phenomenal thing to sort of look at, to squeeze all of the things that we have in there. Quite a lot of work has been done. And certainly you can have a look at the specifications on the projectaria.com webpage. But needless to say, there's some things I'll just breeze through. So there's 2 cameras for doing SLAM, a very wide field of view. There's a very high resolution RGB camera. There's 2 eye tracking cameras to the left and right eyes. There's 7 microphones to pick up spatial audio, which is very important to disambiguate different sort of sounds going on in the environment and from the user. There's 2 IMUs. Now, why 2 IMUs? If you don't know what IMU, that's an inertial measurement unit that lets you get gyroscopic and acceleration data. We've got 2 of them because a human has such a high dynamic range of motion, for example, when they're doing salsa dancing, that we've clocked people doing around 800 degrees per second. That's, you can think about how fast that is to do. And realistically, a single IMU cannot capture both the dynamic range of that motion and also sort of like the resolution that's needed to disambiguate different sort of interactions. So we're really pushing at the limits on hardware together with storage and various different comms to enable Bluetooth and Wi-Fi, etc., to connect to computers and take the data from them and essentially build these new data sets, which we call egocentric data sets. We've been going around ICCV, CVPR. We've got a tutorial on Monday for folks who want to sign up and come and have a look at the new tools and various things you can do with Aria. And we're starting to get a lot of partners. So over 40 odd partners from universities are using these devices with their labs. Investing in the community is key because honestly, these problems can't really be solved in isolation, and yet the community need devices to be able to solve these problems and data sets. So we've been working also very closely with the Ego4D team from Meta and across the university consortium to get that data into the hands of the researchers. Okay, so that's the precursor. Essentially, we need a new generation of device because that's how you're going to get data that's from your real world context all day long, and longer than that. And that's going to generate a new class of computer vision and machine perception problems that have to be solved. So at a high level, these are, and I'm going to go through each of them, building algorithms that basically compress reality. So I'm going to show you sort of the rates of data that come from these devices so that you can contemplate sort of like where your current algorithms are and where the field needs to get to when we understand the sort of rates of data coming from egocentric devices all day and potentially over years. And we're going to have to be able to overcome the limitations that are basically very specific to wearable devices when they get down to glasses form factor. So if you like, in the same way that some major innovations had to occur to go from a PC with a GUI, like a Windows with a mouse, to get to a mobile phone. And this was not sort of like this is not a linear sort of drive from a PC and a desktop PC through a laptop into a mobile phone. Some real innovations in the compute and the hardware. The reason to be, the internet needed to exist so that people wanted to carry a phone in their pocket with a screen and a computer all the time, because that was the value proposition. I didn't have to go to an office to use a computer anymore with the internet because it was in my pocket, and that needed 3G to be developed. So a lot of things had to happen to enable mobile phones to be useful more than just the hardware and the screen. And so, we've got our own set of problems that need to be overcome because of the limitations of devices that are wearable. And then we've also got to actually, as a field, introduce this new class of distributed machine perception, which I claim, if you like, is both a problem and possibly the solution to a lot of our problems that we're going to look at today. Okay, so problem one, we've claimed that contextualized AI is really the North Star for the future of computing. It's what we do, combine our wearable machine perception and computer vision systems from things like mixed reality, shrink them into glasses form factor, connect them to AI. What is the sufficient information from your physical reality that you need to get to that AI so that it can answer all of your questions, do whatever it is you want to do with it, and I'm sure you all have your own thoughts about what you would do with an ultimate AI that was with you everywhere you went. Well, one way of looking at this is to say, certainly you as a human have all the context that you need for yourself from your life. And that's because you have your eyes and your ears and your hands and your body that moves you in the spaces, and your senses go with you wherever you go. Now, these wearable glasses also will go with you wherever you go, and they generate this kind of data. So 150 degrees of field of view of these SLAM cameras and RGB cameras, these 7 micron arrays, this IMU data. Okay, when you total it all up, even when you add on something like 10x compression from really high-end H.264 systems, you end up at nearly a terabyte of data per day being generated from these egocentric glasses like Aria. It's a terabyte a day for just one person. Now, I want you to contemplate where a lot of machine learning solutions to computer vision problems have come from. They've come from us building big data sets, possibly annotating them, possibly doing self-supervised learning, and deriving solutions by end-to-end learning. Now, when just one sample of one person's 8-hour day is around 1 terabyte, then the idea of deploying, for example, a transformer class solution to it, when maybe what you actually need is context that's running over multiple weeks to be able to extract those signals, becomes actually implausible. It's not just funny, it's just implausible. You can't hold the data in the data centers. You certainly can't do sort of a quadratic scaling on attention models. Things like perceiver IO, start to become very important as a model to compress reality. But certainly they're still nowhere near sufficient. And I want to point out that a lot of contextualized AI is not going to just be about your individual AI understanding your perspective. At some point, with your family or your colleagues at work, the data that's important is actually the cross product of all of those people interacting in a space. So if you really just wanted, say, 100 people, colleagues working in an office, and to understand how AI may be brought to bear on their egocentric devices one day in the future, you want to work on the algorithms. Well, we're talking about 31 petabytes of data just for 100 people, just over a year. Okay, so that's never going to be in data centers. Well, maybe quantum computers and some new class of storage and so on, and a lot of hand waving away, maybe. But certainly today, if you wanted to collect that, you would not be able to easily move that data around. The best thing to do would probably be to get FedEx to move it physically rather than send it over the internet, for example, let alone it sit in your sort of GPU memory. Okay, so that's something to really think about. So how are we going to compress that reality? Because that is all of the signal. There is no more signal than that in your physical reality that we can capture. We can get more things like heart rate. We can add a bit more of a sensor, but these are the high bandwidth sensors, the computer vision sensors predominantly. So I basically claim that a lot of the problems we've been working on in machine perception are really problems about compressing reality. And if we can do that well, then maybe we can generate a new class of data that machine learning approaches can be brought to bear on, and that's the way to go. So, can we do essentially world and user state estimation with machine perception to compress reality? And those signals, I want you to start thinking about this from this point of view. What are those signals? What would your AI need to know about you and the things around you that would be sufficient so you could just throw away all of the raw data? Now, it sounds ludicrous, of course, because that raw data is lovely and we like to do end-to-end learning. But if you follow the argument I've just made, you're not going to be able to do end-to-end learning on that raw data without some major innovations in, basically machine learning models. And so an alternative, certainly for the medium term, is to process that data into what we think of as a state of reality, and then start to derive essentially signals and machine learning approaches on that. So where am I might be very important. Do I need the entire image once I know where I am and where I am looking and what I am saying? And that I'm saying it and not you're saying it, so that's an important problem. My kinematic state and all of your kinematic states, you're looking in this direction, I'm looking in that direction, my hands are flailing. What I'm interacting with, the objects I'm interacting with versus absolutely all the other stuff in reality. What's more important? Possibly the stuff I'm interacting with is more important to me. Other states, etc. So not just my information, but also information about you. And of course, that needs to be bridged with security and privacy and consent. But if you did have that, I wonder how long that list would be for you to say, if I had that, honestly, I don't need that raw data. That's an interesting point, because then these become the problems for us to solve, and for us to solve efficiently on the device to compress the state of reality in real time, so it can be brought to bear on our contextualized AI. And of course, all of this is over different lengths of time. If you've ever had any sort of like training injury, you will know the difference between your gait as you walk around, when you are healthy, and then what happens with your sort of limp, etc. Well, this is observable in that kinematic state without those raw pixels, but you might need months of data to know what normal is for you. Okay, that's several orders of magnitude compression right there. If only we can solve all those problems in real time. And machine perception is starting to work. So good old feature tracking that essentially says, this is the same point in space over time, really underpins a lot of our machine perception algorithms. Here you can see the sort of stuff that we do with Project Aria, and basically get these very high quality trajectories. That then gets turned into SLAM maps. So this is a Project Aria device walking around a city block up in Seattle. You don't really need LiDARs anymore. Good quality SLAM systems with that kind of data is sufficient to build this kind of low-level geometry signal that's very useful for other tasks. The same for making the location signal work everywhere. So recently our team's been working on getting Project Aria to work not just in these frames of reference where you walk around, what we call a static equals inertial frame of reference, where the IMU and the visual system agree with each other, but in things like cars, where what you see internally and what you see externally causes a different frame of reference. And so you actually have to think about the two frames of reference and solve for that pose. So we recently had exactly a partnership with BMW that you can see online, actually posted from Mark. We're also starting to get used to the idea that we can just get 3D geometry, pretty good. This is from Project Aria's RGB camera pushed through Nerf Studio, which is available to everybody, using the trajectory from Aria, and then just reconstructing, a lowish quality, but certainly much better than used to be available only a decade ago, basically 3D reconstruction of an indoor environment. Now, that may be sufficient for geometric reasoning. It certainly isn't good enough for computational photography, but it starts to point out that wearable devices can produce signals that are good enough for this kind of state compression. There's a lot of compression going into that model that otherwise would be, basically gigabytes of video data. And what about user state? Well, some work recently from Raul and Chris Katani's lab at CMU with us basically shows starting to get full body state. And here we start to see the first hints of, if there are multiple people with multiple devices, then you can start to get more information than is available from a single egocentric view alone. And that's very useful because then you can start to essentially collapse the uncertainty that exists from just a single perspective. So here we see basically people's entire kinematic body chain being estimated. This is the Ego Humans work that will be at ICCV this year. And then there's these new signals that are actually really, really important, and yet they're absolutely new to the communities because the devices haven't existed. Eye tracking. So here you can see a Project Aria device being used with somebody simply looking at a checkerboard as we calibrate the device. This is called smooth pursuit. Now, when anybody looks out into the world, you may not know this, but there's really only about 2 degrees of field of view that you actually see in high resolution. Everything else is actually a very low resolution. And that's interesting from a compression point of view, because what's important to you, whilst you might think that you see this entirely high resolution world, actually can only be within that 2 degree-ish field of view, and then a lot of motion and lower resolution information in the periphery. So this can drive a front end of machine perception about what might be in the contents of a user's mind. And certainly you don't necessarily need all of that 150 degrees field of view all of the time. And when we see that in application with a modern segmentation algorithm like segment anything model from Meta AI, you start to see the power. So this is Aria being driven with the eye tracking, basically prompting the segment anything model. And you start to see just how thin the context might be in terms of sparse signal. What am I looking at before I touch? Humans always look before they touch if they're not visually impaired. So where you are going to pick up anything is always predated by basically a saccade to that object. This is how sparse the information stream may be, and how we can get over those 31 petabytes down to maybe just gigabytes for years of basically interactions. Very exciting times. So that's problem one, basically build algorithms that enable compression of reality. Problem two is, how do you do that in these wearable form factors? Because it's one thing to do it at all. It's another thing to do it in devices that you have to wear all day. And essentially, this is, some numbers that may not be that interesting to a lot of us. Certainly, I never used to worry about this. I used to think this was just a product problem. I now realize this is the fundamental research problem. We can build devices that compress reality and cameras as big as sort of like, this. And they can do incredible capture for mixed reality. But if you want to shrink that into something that's on my head, it actually becomes a different problem. It's a different research area. It's not just an incremental progress to get there. So, Aria today, 70 grams, it's got 2.5 watt-hours of battery. Your phone, for reference, already has 10 watt-hours of battery. And yet we want it to do a lot more than your phone does. And yet, it's got 1/4 of the power. And actually, we want to shrink it down to sort of 30 grams, like a normal pair of glasses. And we need to get it down to something more like 1 watt-hour, so that it doesn't have the big chunky sides that Aria has, where the batteries go. We want to go basically, again, from Aria to something that you could actually wear all day. And how are we going to do that is the big question. Now, I'm going to, if you leave here with anything, I'm going to leave you with this simple number. I'm going to try and tangibly get the idea of like where the next generation problems really hit, and that's to do with power. What is 1 watt? Now, I've just said your phone has 10 watt-hours of battery. Okay, that's like a number. If you think of it, it sort of takes a device that looks about that big. If they could shrink it, they would. If they could make it thinner, they would. That's the chemistry that requires a battery about this big in your phone. We can't put that on a pair of glasses. It just doesn't fit. In fact, we think what you've got available is about 1/10 of that. Okay, 1 watt-hour. Now, it needs to work over a 10-hour day, just like your phones now do. Otherwise, it's very annoying when the device stops working. And anything that's doing all this machine perception has to be done possibly in about 10% of the battery, because otherwise, what's the application that the person's using? Are they connected to the internet? Are they streaming? Are they looking up something and asking a question to an AI on a cloud? That's the 90% of the 1 watt that you've got available. So you've got 100 milliwatts over 10 hours to solve all of that machine perception. And if you can't do that, then you can't have always on AI that connects your physical state and your AI together. That is the fundamental challenge that we're dealing with. Put it into perspective, go and have a look how big your GPU power is, and think about how many orders of magnitude that we've got to get where we are going. To solve it, we've got to solve sensing, compute optimization, memory optimization, new classes of memory that really understand the algorithms, and the data transmission and reception problem. We can't just send all this data off board. That actually burns more power than processing it on the device. And we may hear some more things about that today. And all of that is going to be driven by this co-design with algorithms. So when you do fundamentally understand that 100 milliwatt per day constraint, you will start to look at algorithms in a very different way. You'll start to think about the sensors in a way which causes you to think, why don't I have this other kind of sensor, like event cameras? Why aren't I using those in my algorithms if really what I want is always on machine perception and things like that? Okay, but there's more to this problem. Problem 2 is not just about power and compute. It's about the fundamental limits on sensing on wearable devices. We are now used to taking beautiful photographs that look like this. Well, take again your phone out your pocket and have a look at what the sensor array looks like. These now 3 on my S22, the 4 that I think are on an S20 or 6 that are on an S24, same with like high-end iPhones, they are not there arbitrarily. It's because there is a physical limit on capturing optical information, invisible light spectrum, that requires sensors of this size, lenses and pixel sizes. And ultimately, you can think of it as a machine perception challenge like this. If your glasses cannot see what you see, they're going to be really annoying in a lot of situations where you're asking your AI, about, something on a menu. And it's like, oh, I can't see it. Could you read it for me? And you're like, well, I can, but I wish you could just have read it already. So 2020, in case you're wondering, is the specification of a 1 arc-minute resolution. It's an optical resolution. Doesn't matter how many pixels you've got underneath it. Measuring it is about basically the fidelity of optical information. That's what humans with corrected vision can do. And so we're trying to aim for that. Now, you also want high resolution, large depth of focus. You want low noise in low light. You want this incredible no motion blur situation that we're now all used to when we make beautiful videos, right? And you want this incredible high dynamic range. And, the thing is, we've got to fit it again in that form factor. And you can see our Aria device has got these big circles on it that look a bit like the things on the back of your phone, right? That's not arbitrary. To get from basically Aria to something that is always on wearable and not with those big circles is going to take some breakthroughs in machine perception and sensing. And the reason is because basically to shrink those sensors is to try and overcome the fact that you as a human who does achieve 2020 require eyeballs, and eyeballs are not arbitrary. The eyeball is the optimized size for you, and not just you, but also eagles, and actually at the other end of the spectrum, owls that are basically in low light and high light. They are optimal for the refractive optics for visible light. And when you try and get smaller than that, you start to trade off with optical resolution. Basically, you get to what's called the diffraction limit on optical sensing, which is the point at which basically the wavelengths of light don't get through the aperture. And that size is 2 millimeters. And any sensor lens configuration smaller than that is going to blur the image. So think about that for a second. You cannot get smaller really than an eyeball and not start to lose something. And of course, your eyes move around. They've got this little other thing. So if we're going to replace eyeballs or at least augment them with glasses, we've got some real challenges to enable the resolution and the depth of focus, etc. That's a specification on an eyeball, and we need to be able to put something like that on glasses. Obviously, there's some sort of conflict of what is possible there. Okay, finally, problem 3, which I think is possibly the solution. Now, I brought you these today because I thought this community, and certainly the community I'm from, which was building high quality 3D reconstruction, solving SLAM problems and doing it for mixed reality, would be interested in the fact that those problems are kind of really getting solved now to the point that you can buy them in products. Lots more interesting things to do. We're going to see it today. But honestly, if you want to get to always on AI, you're going to have to confront the wearability constraints that come from glasses and the machine perception algorithms that are going to be suitable for them. And one possible space of solutions is what we can think of as a distributed machine perception. And for this, you can think about the multiple people, even in this room, that are distributed in space, but we're all in the same temporal frame of reference. And we all have a little bit of sensing. If we have a device that we're wearing, we all have a little bit of compute if we're wearing wearable computers. And some people are closer to the menu than I am. And so these constraints on optics and basically field of view and resolution and compute and inference, for example, something has already been detected in the environment. Does my device need to redetect it in the environment, or is it okay to allow that to have been distributed to another device and cache it in a model of reality? So think about this space-time continuum of devices and how they are the sensing platform of the future. And so the computer vision algorithms and machine perception we need to work on needs to really unlock that potential, because I can tell you there are no solutions to the wearable single device glasses problem that we've seen today. Okay, so just to close, I want to claim, my final claim, that really the most exciting breakthroughs that are going to come next in computer vision, and therefore the research opportunities, if you are doing your PhDs and so on right now, are in this space. And basically, this is required to unlock contextualized AI, and it's contextualized AI that's going to unlock the second great wave of human-oriented computing. Thank you.
We have the mic WhatsApp questions. If there are questions on the Zoom, I can bring it up.
Yes. Lots of thoughts, lots of, yeah, there's a question. It started off.
Yeah, you were mentioning that multiple AI classes interact with each other.
Mm-hmm.
Are you also thinking to use some fixed install sensors, for instance, in the home or in an office?
So this is a very good question. This is the infrastructure versus egocentric question. This particular work from Raul and Chris Catani's team kind of points out that today, if you do have some amount of infrastructure, so what's actually going on here in the Ego Humans paper is we have everyone wearing an ARIA device. They, of course, are like continuously moving infrastructure. So that's nice. But we also have some GoPros around. So that's the different sort of sticks you can see. And that really does help currently solve a lot of these problems. The thing is that the resolution that you can get from infrastructured cameras, if you think about things like an OptiTrack system, actually become very limited very, very quickly unless you're willing to completely plaster all parts of the surface with those cameras. It's just the way that basically camera geometry works. So you can't get a high enough resolution sensor and start to put them everywhere in all people's environments. The data bandwidth from that data, of course, is very difficult. And ultimately, where you are is probably where the most important information is. So if you carry your infrastructure with you, if you like, then that's possibly the most elegant solution. Occlusion is a problem with infrastructure. Resolution is a problem. Bandwidth is a problem. Privacy concerns of bystanders is also a problem. It goes on. And so in some ways, the fundamental solution is actually you carry your infrastructure with you. Yeah, good question.
Hi, thank you very much for the talk. The way that you described learning now using we're using the ARIA glasses, is that you're describing a system now in which all the learning will be based on the devices themselves and the collaboration between them. Mm-hmm. However, do you think that there is space for learning in which, for example, denser or higher resolution signals are getting from the devices? They are processed somewhere in centers, and then some of the models then are transferred into the glasses, because you don't need to learn everything on the glass themselves. Yeah, you have a lot of things that are on the internet already. There are a lot of things that are on the web. Yeah, how do you think that? What do you think this balance?
What I think about this figure, and I think about what enables the solution of multiple devices to become the sensory and compute nodes, and the answer to that question is something that we historically have called live maps, that enables multiple devices to connect to a distributed infrastructure where some of that is actually shared on edge, some of it is in cloud, and that a lot of the information in reality is really not changing at all. So a very good sort of like skeuomorphism to the concept of a map is suddenly, apparent. So if I could build a map or a model of reality, effectively, that's where a lot of the information is. I simply need to read. I don't need to process anything on this device. Now, a model of reality, as Jan LeCun has also talked about, in the last year and a bit, doesn't need to necessarily be sort of like a 3D model necessarily. It can be a machine learning model. And, that's, of course, what we're seeing with modern large language models that have been trained off corpuses of the internet. So exactly right. And a lot of that is like where we need to get to. And the ultimate thing is that each of these devices, space and time observations, think of those as like publishing the web pages of a new generation for, large language models that is built on machine perception data rather than sort of text of blogs and Reddits and so on and Wikipedia entries. But otherwise, the paradigm is the same. You're exactly right. Thank you, everyone.
Deanne, are you there? Can you
Yeah.
hear us?
Okay. Yeah, I can hear. I'll start screen sharing.
You're not muted, right? But we can't hear you.
Hello? Can you hear me?
Just if you plug out, just on your
Hello?
laptop, do you hear it?
Oh, I'm not muted.
We can hear you.
Can you say something, Deanne?
Hello? Hello?
No?
Just settings, try to maybe as output. Sorry.
Settings.
Basically, the top. Okay. This is the speaker.
Hello? Can you hear me? Hello?
Hey, we can hear you.
Yeah, is it from the workshop? So, or just Zoom? Stephen, are you virtual or in the workshop?
No, I'm just I'm not from the workshop. I'm just here for seeing the
Ah,
workshop.
I see. Because I think people in the workshop I can like they can talk, but I cannot hear anything from them. And previously they couldn't hear from us. So yeah, that's why I'm still waiting for their confirmation.
Oh, okay, I see.
Yeah.
Sorry for confusing you.
No problem. No. Hi everyone. I'm Dean from NVIDIA. I'm not very sure who can hear me, who cannot, but I'll just go ahead. And thanks, Richard, for the great keynote. Very excited about project area. Now I'll switch gear to one of the technical area. And the title of my talk is Annotation Efficient Scene Understanding. So scene understanding can mean a lot of things, but in this talk, I'll just focus on 2D segmentation, which still has a lot of application and serve as the first stage for a lot of later processing. And yeah, it still has a lot of applications. For example, on the left for mixed reality, it might be very helpful to understand what are objects in a scene for re-rendering a scene. And another well-known application is for self-driving, for segmenting all the cars, the roads for planning. But one of the downside of this, the 2D segmentation is it requires expensive pixel annotation. So the goal of annotation efficiency and understanding is to find ways to reduce the cost of scene understanding and 2D segmentation. And today I'll talk about 3 works from our group. The first is box supervised image segmentation. In training, we only annotate boxes, and in test time, we can output segmentation mask. In this case, the annotation cost is much cheaper. Annotating box is much easier than annotating mask. And once we have image segmentation, the next work I'll talk about will try to go from image segmentation to video segmentation without any additional annotation. Finally, if we first put the first 2 pieces together, we kind of have a way to go from box supervision to video segmentation. And for the third work I'll talk about will explore pushing a step further and explore point supervision for video segmentation. Now I'll start from box supervised image segmentation. And the title of the work is Vision Transformers Are Good Mask Auto Labor, which is led by my colleague Si Lan. And here is an overview of mask auto labor. And the most important, there are two important things from this overview. First, the whole framework is split into two phases. And the actual instance segmentation or the segmentation model training is only in phase 2. The reason is that there are many state-of-the-art segmentation models, and they're quite different. Some are 2 stages, use bounding boxes. Some of them they're 1 stage and output all the masks at once. We don't want to put constraints on what kind of instance segmentation model you want to use for the task. So instead, what we do is we focus on generating mask labels or pseudo label from the annotated boxes. And once we produce these pseudo labels, the user can just take whatever their favorite model and train a segmentation system. And the second important thing is because we can sort of do whatever in phase 1, we're not constrained by state-of-the-art architecture. One of our design decision is to work with crop regions. Just work with each of the bounding box independently so that they don't interfere with each other. And here is the overview of the framework. There are many things going on. I'll just give a few highlights. The first thing is we're doing per box processing, as I mentioned. And the input to the model is not just the very tight crop region. We sort of expand it a little bit to include some background as hard negatives. And this bounding box will pass through image encoder and a mask decoder. The encoder part is a pre-trained transformer. So the pre-trained thing is important. We cannot do this work with encoder from scratch. Like even supervised training, self-supervised training, anything will really help. And I think a lot of you are probably familiar with Dino, like the emerging properties of transformers. That's kind of one of the things we're leveraging here to make this box supervised mass auto label work. And the second component is for the decoder, we tried different architectures and found that this attention-based mass decoder is important for the performance. And once we have the input and pass it to the model, finally we need a good loss function to still go from the box to supervised pixel understanding. And the main loss we use is multiple instance learning. Here, here, each of the bag in multiple instance learning is either a row or a column in the image. And a bag is positive if it passed through the ground truth mask. And we know it by if it passed through the ground truth bounding box. So that's sort of we put all these pieces together and then have mass auto labor. And some more details about the design. I guess I already talked about our back sampling strategy, what are positive bags and what are negative bags for our multiple instance learning. And for mass decoder, we use attention-based design. So in the first sub-figure, the green one, is using NLP. It's not a good design. We try it out. So basically just from a vector, you expand it and directly get the mask. It's not a good design. And B is fully convolutional. It's much more common in segmentation. But what we found to be the most useful is in C, this attention-based design. You have basically you have 2 heads. One you produce the key, and the other you produce the value. And the key you just scan through the feature map to get the segmentation map. And then one more detail is because the classes that go with the bounding box, we don't the whole mask generation from box is class agnostic. So let's look at some qualitative results. The main thing on the top is output from masked auto labeler, and the bottom is, I think, is Cocoa annotated ground truth. And the main thing we want to highlight is, interestingly, for a lot of cases, our pseudo label is tighter than the annotated ground truth. I think similar things are also observed in the segment anything paper. Sort of the machine predicted ones, masks are tighter than human annotation. And in terms of the quantitative results, there are two parts to this table. There's the top part is they're all mass supervised, fully supervised, and the bottom part are the counterparts using our box supervision. So there's a one-to-one correspondence for these two parts. And the most important, most interesting metric to look at is are the last two rows, the retention. So sort of how much performance we retain compared to fully supervised. I think, and from the result, we can see we can retain up to almost 95% of the performance of mass supervision. But our method is only really using bounding box as supervision, which is much cheaper than annotating masks. So now I talk about box supervised image segmentation, and next I'll talk about how we can move from image segmentation to video segmentation without additional cost. And the title of the work is MIN-VIS, a minimal video instant segmentation framework without video-based training. So here the assumption is we already have an image segmentation model. We already trained a good image segmentation model. Kind of ignore what the model actually looks like. From an input frame T, we pass it through the model, and then you can segmentation the objects inside the frame. Here there is a person and a skateboard. And we can do it similarly for another frame independently, this input T+1. We can also apply the trained image segmentation model to segment the person and again segment the skateboard. And what I've mentioned is just image segmentation. To go from image segmentation to video segmentation, what we need in addition is tracking. We need to know the person in frame T is the same person in frame T+1. And we don't want to match the person to the skateboard. And we don't want to, and this they might seem kind of easy, but in a lot the actual video segmentation data sets or applications, imagine there are like 10, 20 people, and you need to do this same tracking temporal correspondence, then it's much more challenging. And what we have found in this work, the most important takeaway is if you train a really good image segmentation model, then its intermediate features are already sufficient for you to do tracking across time. And in this case, during training, you don't need to do anything specific about video. Just at test time, you look at those intermediate features and use it for tracking during inference. And more specifically, what we're using is the queries. So at the high level, each query is like an exemplar vector for an object. In more details, we use a query-based instant segmentation model, which now I'll give an overview of that. And given an input frame, first, very standard, you pass through an image encoder to extract feature maps. And the other component of query-based instant segmentation is this transformer decoder. It'll start from some initial queries, each is a vector, and process it jointly with the features using cross attention. Eventually come up with this, in this example, 3 query vectors. And then these queries, you can just convolute it with the features to generate the eventual the output mask. So here, the red query, the third query, it's an example of a person. Then when it's scanning through the feature map, it will have high response for pixels corresponding to the person. And the queries is also used for classification as well. So that's queries. Queries basically capture each of the query correspond to an object in the scene. And what we found is to do tracking at test time, all you need to do is to do bipartite matching of these queries, and you can track objects, even object instances, very well across time. And this is also the case for the more challenging scenarios I mentioned, like 10, 20 people in the scene, or animals, or sheep, fish. It still works. And sort of to support the idea, we do some more visualization of the learned query embeddings. The whole training is only done for image segmentation, and we apply it on videos. Here, every point is a query, and queries belonging to the same object are colored the same. And because it's video, so there are many frames and many queries corresponding to the same object. And what we can see from this Disney visualization is points or queries corresponding to the same object. They are already grouped together temporally, even though we only train with image segmentation objective. This is also the case for two other more complicated datasets. And one benefit of this is when we're doing video segmentation, which the annotation cost is much higher. Even like 1 second or 2 second video, the annotation cost might be 10x, 20x compared to image segmentation. Using our framework, what you can do is, because we only use image segmentation training, you can just pick whichever frame you want to annotate. In this specific example, for 10 frame video, we can pick 2 frames to annotate. And this greatly reduced the annotation cost. And for quantitative results, here the y-axis is the AP, and the x-axis will be different methods. And this baseline mask2 former is one of the state-of-the-art method when we're working on this project. And it can be considered as a per clip counterpart of our method. And our main VIS significantly outperformed the per clip baseline counterpart. And more interestingly, with only 1% of frames labeled, we're already kind of comparable to the previous baseline. And with 10% of frames labeled, we're approaching our own fully supervised number. So this really shows sort of like there's a trade-off, but of like allocation cost and performance, but it's a pretty good trade-off here. And now I've talked about how we go from image segmentation to video segmentation. And finally, I'll sort of put things together and talk about our recent effort on trying to use point supervision for video segmentation. And the title is, what is point supervision worth in video instance segmentation? And again, here is the overview, and we do the same two-phase design as mask auto label. The first phase we do pseudo label generation, and once we have the pseudo label, we can use it to train the video segmentation model. Although in this case, we do use the same architecture in pseudo label generation and video segmentation. But I'll just focus on pseudo label generation here. So in order to generate the spatial temporal pseudo label from input frames, there are two things we'll need. The first is class agnostic mask proposal. So this is something we assume we already have, which we can get it from various sources, either foundation models or maybe using the same assumption, we already train an image segmentation model or whatever sources we have. But we assume there are already some kind of object-based pixel grouping here. And the other thing is the point annotation. So point annotation in this case means for each object in each frame, we just have one click on the object. And this click, there's still the temporal correspondence. We still track the point across time on the object. And once we have these two things, we'll put them together into a spatial temporal point matcher to generate our pseudo label, pseudo mask label. And sort of just high level overview of what's in the spatial temporal matcher. The first important step we do is to transform the class agnostic mask proposal for each frame and connect them across time to generate a lot of spatial temporal mask proposal. So instead of mask in individual frame, imagine now you have some tubes, spatial temporal tubes, proposal of object in a video. And in our work, we use a query-based mask proposal for each frame. So similar to the previous work I was talking about MinBIS, we just do query-based matching to generate this spatial temporal mask proposal. And to generate the pseudo label, all we have to do is now we have these spatial temporal tubes, right? A lot of spatial temporal tubes. Also, we have a lot of annotated point trajectories in spacetime. So what we have to do is just to match the point trajectories to these spatial temporal tubes. And the ones that are matched to the point trajectories are used as our pseudo label. So we just do bipartite matching, but in the score, we need a score, like a score function to do the matching. And the scoring consider three things in our score. The first thing is annotation consistency. So let's say I have a spatial temporal tube, and I want to compute its score to the horse point trajectory. Then one very important thing is this tube should contain all the points annotated for the horse. And that's annotation consistency. And the second component is we call it cross-negative consistency, meaning if this tube has a high score to horse, then it should not contain the point trajectories for person or all the other instances, if there are several horses. And finally, each tube by itself, it has a maskness score when we want to prioritize high priority spatial temporal tubes. So using these three criteria, we can have a score, pairwise score, and using that score, we can run bipartite matching, and the spatial temporal tubes that's matched to the point annotation are used as our generated pseudo-ground truth. And these are some the qualitative results of our generated mask label. And here you can see the annotated points are in circle, and you can see although there are like the third round there are 7 dots in the thing, we can still generate pretty high quality pseudo mask label. So this really shows if you have some way of getting some kind of pixel grouping in each frame, will like applying this what you have to obtain video segmentation for novel classes in new scenario is actually not that expensive. You just need a couple clicks, and then you can get really high quality video segmentation. And in terms of numbers, again, there are two parts. These are just two data sets, and the first three rows are fully supervised by mask, and the third row is the min VIS work I just talked about. And for the point supervised ones, we have two variations. The first one is P1, the fourth row, meaning for each object in each frame, we just have one positive click saying this point belongs to the object. And the second variation is P1 and 1, meaning one positive point and one negative point, 1 point inside the object and 1 point outside the object. And again, the most interesting number to me is the retention rate, like how much performance we're retaining going from mask supervision to point supervision. And on the first data set, we can see with only one positive point, we're retaining almost 88% of the performance. And the annotation cost is much cheaper, like just one click on the object instead of annotating the whole mask. And more importantly, is the gap between P1 and 1 and P1 is large, meaning having an additional negative Q is very important. It's just one additional click outside the object, it brings up the retention by 9%. So, but still a very low cost compared to annotating the whole mask. And I think that's mostly what I'm covering for annotation efficiency and understanding. First, we have a box supervised image segmentation model. And once we have an image segmentation model, we can move on to video segmentation without additional annotation costs. And finally, we can put all this together with a very cheap point annotation to do video segmentation. And finally, I just want to briefly touch on the segment anything model. If you're remotely interested in segmentation, you probably know the segment anything model. And Richard also mentioned this work in the previous keynote. And if you're don't know what it is, essentially it's a foundation model for segmentation by prompting. You have a foundation model for segmentation, and the prompts can be point, box, mask, or text. And it has shown really good performance in a lot of real-world scenarios. So the question is, okay, we have this foundation model. Do we still need annotation efficiency and understanding? I think this is still something I'm exploring, trying to figure out, and really open question for anyone who used to work on segmentation. Yeah. And for me, scaling up segmentation data is definitely much harder compared to a lot of the other areas we have seen. And more specifically for the works I talk about, one of the work I talk about focus on video and tracking. For me, I think now is really a good time to work on tracking. What we have shown is not that we don't need temporal supervision at all. What we have shown is really better image understanding can help you do much better tracking and temporal modeling. And with this segment anything model, you really have much more fine-grained image understanding, and there are many exciting things we can do in temporally for like video segmentation or tracking. And for the box and point supervision work I talk about, I sort of picked them specifically because they can be used for prompting the segment anything model. I think one of the things I want to mention is just sort of for box and points, one way to look at it is they are just prompts. But the other way to look at it is they can also provide complementary supervision and can also make the model better. So I'm also still exploring what are the good ways to use box and points in segmentation. And yeah, that's it. Thank you.
Um,
There a charger also. I have my own.
Sorry, it's in the system.
Okay, very good. That's it.
yeah.
Right.
Yeah, late. Sure.
Yeah.
No, I think there is one more answer. Oh, there is like no.
This, yeah, go there, maybe a page, the guys. Make sure that this. And then this one. That's the one.
This meeting is being recorded.
Yes.
Okay.
And then just the audio as well.
Is the transcript.
Can you say something?
Well, is audio and Zoom working?
Uh,
No.
no.
I need the settings program.
Oh, in the settings, you might have to change the.
Oh, wait. Hello, is that better?
Yeah, what was that? What was the problem?
No.
Okay, screen share and everything's working on Zoom?
Yes, all of the issues that we're running into today. So our next speaker is Pratul. I guess many of you, most of you know already about him through all of the work that he has done in neural radiance field. Pratul is a research scientist at Google. Prior to Google, he did his PhD from UC Berkeley, where he was the recipient of multiple awards for his dissertation work on neural radiance field, and he would be presenting some of his recent work here. Thank you.
Yeah, thanks for the nice intro. Yes, I guess I don't need to go through any of this, but I work on a small team at Google Research. Meldon Hall, Dora Verben, and Peter Hedman. And we work on all kinds of problems related to inverse rendering, 3D object and scene capture, and specifically methods using neural radiance fields or trying to extend NeRFs or neural radiance fields to be a general purpose representation for 3D content captured from real observed images. Cool, yeah, so let's get started. So yeah, again, most of the projects we work on are related to neural radiance fields or NeRFs, which are volumetric scene representation that's particularly good at the task of view synthesis, where we observe a sparse set of images of a scene, like these orchids on the left, which the video should look jerky because there's just a subsampled number of images. And we have the camera poses, novel unobserved viewpoints, like we're visualizing in these hopefully smooth video rendering on the right. Cool, yeah, so NeRF's a neural volumetric scene representation, and I'll just do a really quick getting into more recent projects. So you can, the basic idea of NeRF is that you take a, represents a scene as a neural volume where you, and viewing direction, which is denoted as theta phi here, and you pass them to an MLP or some other neural network, and it tells you what is the view-dependent emitted color of particles at that location along that direction, as well as the volume density. And so you can query a bunch of points along any array corresponding to a camera, combine them all using standard volume rendering techniques, and render the color of an array or color of an image. And you supervise, you train this NeRF model by just minimizing the re-rendering loss, right? So you can take your current state of parameters of the network, render the color of pixels for images that you've observed, and then just minimize the loss between these re-rendering images. And in the original NeRF work, we were able to render kind of arbitrary views of these small toyish objects, synthetic objects floating in space, as well as more limited viewpoint ranges of scenes that are more complex and unbounded, but note that the range of viewpoints we could actually re-render was pretty limited. Okay, so there's been a lot of progress over the last 3 years, and I just want to talk about some of our work to improve and extend NeRF as a more general representation of 3D content that you can recover from observed images. And one of the main goals of our group has been extending NeRF to capture more rich and immersive full 3D environments rather than just these like limited windows into a big 3D scene that we saw before. So nowadays we have like these capture setups where you can take a camera, wander around the scene maybe for 10 to 15 minutes, like you're seeing Peter walk through. You can take thousands of pictures of these large scale scenes. And then from this data, we're able to create these really nice like full 3D reconstructions that allow you to render high quality, high resolution images. Sorry if this camera path makes anyone a little dizzy. There's a lot of roll in the camera path here. But here's a fly through video that's rendered out at like 1080p from a NeRF that we've reconstructed of that scene from I think about 1,000 images. And we can do more than just render videos, right? Like there's a full 3D representation. So here's like a lower resolution but interactive visualization that's demonstrating we can do like full. And a caveat that I'll get into is for now, these are still running on like really serious server class GPUs, right? So these frames are rendered at a slow but interactive rate on 8 V100s. So that naturally leads us to ask how we compress or rework a NeRF-like representation to be able to render high resolution images, but ideally in real time on more accessible consumer hardware for maybe potential use in mixed reality applications or something like that. And we have a couple of research projects that kind of have made some progress towards this goal. And here's a demo of
one of them, which is real-time rendering on a phone, while maintaining pretty high quality of a volumetric NeRF-like representation. And then finally, I think a lot of the 3D content we really care about viewing in AR, VR, such people are dynamic, and we've been working on a few ways of recovering NeRF-like models of dynamic human appearance that I'll get into, hopefully if we have time at the end. And I'll still want to talk a little bit about a project that uses unstructured photo collections of a person. Like here, if you just Google images of Roger Federer, you can use an unstructured set of like 20 images of him to get these NeRF models that can render his appearance across, his varying appearance across like different times and body poses. Cool. Yeah, so I'll talk about those kind of 3 things. So I was talking a little bit about capturing full 3D environments with NeRF, compressing them for more memory efficient real-time rendering. And then if we have time, I'll get into capturing dynamic human appearance with NeRF. Cool, so we started working on this direction of extending NeRF to render large unconstrained views of big scenes with this MITNER 360 paper that we worked on last year. So I was going to quickly go through that before getting to a newer follow-up. So MITNER 360 investigated how to deal with these unbounded scenes. And by unbounded, I mean, in this case, like scenes where there's a main object of interest, like this table with the flowers on top of it, and the camera is rotating around it, but you're still observing content that can go all the way to infinity. And there's 2 main problems when you take like a basic NeRF-like model and extend it to represent these larger scale scenes. And the first one is in terms of parameterization, because unbounded scenes are unbounded, but NeRF needs inputs in a bounded space to be able to work well. And then maybe a bigger problem is that these scenes are really detailed and the high resolution 3D content that we wish to represent. And you can fix this by making a NeRF network much bigger, but this is going to make training and rendering much slower. So we need a manageable way to increase the capacity of our representations. Cool, so let's start with parameterization. So here's just a visualization of the problem, right? We have like this toy flatland scene with these 3 cameras. And if you just want to visualize the frustums that are cast by a bundle of camera arrays. And it's clear that these camera arrays kind of sample points that are really far away from the camera. And it's a problem for NeRF-based models, which the MLPs work much better if you have a bounded set of inputs. And that's due to the nature of training MLPs to represent functions. And so kind of a simple idea, just to map them back into a bounded region of space. You can use a warping function. And the one we use here is this identity inside the unit sphere. So you can see like these points visualized in blue, nothing happens to them. And then points outside the unit sphere, they get rescaled back as a function of their inverse norm. There's a little visualization of what's happening. So the key point is that it really matters how you scale these input camera poses, right? So we have these kind of unbounded scenes that we're capturing, these 360 style captures where we kind of walk around a scene and observe content to infinity. And to match with this contraction function, what we're going to do is that we adjust the scale of the camera parameters so that all the input cameras roughly lie on a unit sphere. And this way, the content that's more isotropically observed, right, the stuff that you're kind of walking around and looking at, that gets maintained in this uncontracted blue zone here, right? So like the stuff within radius 1, and then the more distant content that goes out to infinity, all gets warped back into this, the rest of this bounded sphere. Okay, so that's just a quick an issue that you need to take care of when you're representing the unbounded scenes. But the more significant challenge is is capacity. So what we're trying to figure out is like, how can we increase the capacity of a NeRF representation or network without causing a huge drop in performance? And so here's a kind of toy visualization of a NeRF network. You're representing this bunny here. If you want to represent a higher more detailed environment by increasing the size of the network, to maintain the same computational costs, you're going to have to reduce the number of samples per array, right? But then where you put these samples becomes really crucial if you want to maintain the same quality of rendering. And so to fix this, we're introducing a small proposal network. So this is like a lightweight MLP that's way faster to evaluate than a big standard NeRF network. And it's going to tell us what regions of space need to be sampled. And we can visualize like the output of this network as these green bars here. So it has like a distribution over where should I sample a long array. And so you can interpret this as a probability distribution and redraw some more samples from it. And hopefully, if you do this multiple iterations, And if the proposal network is working well, it'll cluster the samples. The resamples that you get should be clustered around the visible surfaces. And you can, at training time, you can supervise the weights of this MLP to match the scene geometry that's recovered by like this larger NERF network. So what we do is like we have a small, really fast and easy to evaluate MLP that just tells you these like proposal distributions. And then we do multiple rounds of sampling through that, get a small number of samples along each ray that are hopefully clustered around the stuff that's actually going to make it into the final rendering, the visible stuff. And then you can pass those into this large heavyweight MLP that represents like the high frequency, high fidelity color and density in the scene. And so this lets us increase the size of the NERF network since it needs to be queried for a lot fewer points per ray. And then that allows you to scale to these like large detailed scenes. Cool. And so here's a rendering from that model. And given a couple hundred poses of these posed images of these scenes, you're able to produce these really photorealistic renderings. And I'm also visualizing some depth maps that you can compute. But these results are really cool, but it still takes over a day to train, right? This is a pretty expensive process for these large scenes. And so a few months later, right? So this is a project that we, the MIP NERF 360 project was like in 2022. And a few months after we released that, researchers at NVIDIA came out with this really exciting instant NGP method. And so the main takeaway from here was like you can speed up NERF networks to an incredible degree by using hash grids as a spatial data storage. And just to revisit what's the problem with big MLPs, right? So the particular issue with scaling up MLP networks is that the runtime increases linearly with the number of parameters, right? So to query a representation for a single point in space, you're gonna have to access every single parameter to perform the matrix multiplies that you need to go through an MLP. And this is a really bad property when you want to reconstruct larger and larger scenes, because as you scale up the capacity of your MLP, you're going to still have to touch every single one of the MLP parameters or use them to compute the output of the NERF at any point in space. And so in contrast, grid-based representations, right, like hash grids that are used in instant NGP, enable you to query the model by only accessing a constant number of parameters for every 3D point that you query. So you only need to fetch a few features from a hash grid, maybe like a linear, trilinear interpolation, decode those with a tiny network, and then you're done, right? So in other words, hash grids let you do this like compute for storage trade-off, right? So they decrease the amount of compute you have to do to query the NERF at any point in space at the cost of a little bit of increased storage, but it's still totally manageable. But there's an issue with trying to extend these models to really large scenes, and it's mostly an issue related to aliasing. So the standard NGP models, you still query single infinitesimal rays to render the color of a pixel. And to avoid aliasing issues, what you want to do is render something like the average color of all rays in the footprint of a pixel, right? And there's an easy way to do that by just naive supersampling, right? You can, for every pixel, you can shoot out a bunch of rays and then average the color you get. That's actually going to be quite expensive, and then doesn't really solve our problem that we are taking days to train and hours to render videos for these really high detailed scenes. So instead, we want a more efficient way to do something like rendering this entire cone of rays. And just to visualize what this problem looks like for larger scenes. So if you have like a pretty beefy, nice NGP model, and you're trying to represent this scene, this bike in a park, if you zoom in, you get these zoom in and zoom out, you get these aliasing issues. So you can see that like the spokes of the bike, they kind of shimmer in and out. And when you zoom out, you get the like classic kind of aliasing jaggies artifacts. Okay, so in our latest project we called ZipNERF, we specifically focus on this problem of aliasing in large NGP style models or feature grid style models. And I don't have time, I guess, to go into a lot of the details, but at a high level, what we're going to do is instead of sampling points along an array and then passing them to the hash grid, we're going to construct like a multi-sampling kind of pattern. So we're going to multi-sample features fetched from the hash grid, take the average feature, and then pass that to the MLP. Average in some sense of average. So instead of point sampling the hash grid along the array, again, we're going to fetch from these multiple sample locations that we're visualizing here on the right, and average them in some way before you feed them into the MLP that decodes features in the color and density. And in the paper, we investigate lots of different kind of sampling patterns, and it turns out that these deterministic kind of quasi-random sampling patterns seem to work better than actual random patterns. And so here, for a lot of the results, we use the spiral, and we also have like some hexagon style patterns and other stuff. So let's take another look at this bicycle scene. So if you just do this multi-sampled queries, the results are much more stable, especially on the spokes, right? So you can see what we had before was on top, And now we have, with multi-sampling, doesn't have these as bad aliasing issues. But there's also another source of instability that's related to aliasing again. You can think of this as like aliasing in depth. And that's actually due to the way we trained the proposal MLP back in the previous project, Memory 360 I just talked about. So it turns out that the way that the proposal network was trained caused aliasing along depth, or Z aliasing, you can think of it. And so it made it possible to systematically miss foreground regions. So the idea is like when a camera moves forward a small amount, the uniform samples along the ray that we use for the first round of sampling can easily miss scene content if the underlying distribution represented by the proposal MLP is not smooth enough. Right, so if you kind of move back and forth, you still want to allocate high, kind of a high proposal density to the first visible surface. And so you can actually really visualize this in real data from those old models that we trained. So here's we're kind of on the right side, we're visualizing the rendering weight distributions along the specific ray that's denoted with like this green cross on the left, right? So it's a scene where we're looking at this chair and we're slowly zooming in on the chair. And so if you plot the rendering weight distributions from each round of proposal and NERF network sampling, so on the right, like the legend 1, 2, 3 are different levels of the proposal network, right? I said that we sample this proposal network multiple times in order to compute our final samples through the NERF network. And you're visualizing what the rendering weight distributions are that come out of the proposal network. There's 2 rounds of samples through proposal network, the blue and orange, right, 1 and 2, and the final is the NERF samples. And you're seeing that as the camera moves forward, the blue distribution, which is like the first round proposals, is alternatingly hitting and missing this foreground chair. And then that's what's causing this crazy like striping artifact that's sweeping across the chair as we slowly move the camera. Okay, so in the paper, we focus a lot on fixing this problem. So essentially what we want to do is anti-alias this rendering weight distribution that's used for resampling points along array that's from the proposal network. And then if you just kind of take care to make sure that this network is representing a smoother anti-alias distribution, you get a lot more temporally stable results as you move the camera in the scene. And so in our fixed method, the samples from the blue network, number 1, are actually hitting the foreground object, right, in all the frames in sequence. And now you can use this improvement in aliasing, both spatial XY aliasing and aliasing along Z, to create these cool fly-throughs. So this project really tried to kind of push the limits of what NERF-like models can do to expose some of these problems that we used to have with aliasing. And so here's like a more dramatic looking fly-through through a house. And then here's a little comparison. So our models, again, on the right, and the combination of like our previous model, Memory 360, with NGP NERF representation is on the left. And you can kind of see the aliasing artifacts on the left that you see striping as you move the camera around, and the results on the right should be hopefully a lot more stable. And here's another really cool large scale capture. I think there's about 1,200 images to capture this cafeteria. Okay, so let's think a little about quality versus speed, right? So the last example I showed you, it took about 2 hours to train, but about 7 hours to render, right? So our training was improved a lot by using using instant NGP as the underlying representation, and even making it a little slower with all our anti-aliasing. And so that 7 hours of render is a lot, right? It's like 12 seconds per 1080p frame, even when you're using 8 server class GPUs like U100s. So if you want real-time rendering, it's about like 5,000 times too slow. So yeah, we'd really like to have a more practical method for rendering trained NERF-like models with more reasonable hardware constraints. And that brings me to 2 more recent projects from our group. So both these were led by interns in London in our who interned in our team, and specifically interns Christian Reiser and Lior Yariv. And one of our team members, Peter Hedman, is really into real-time rendering. He's really knowledgeable about image-based rendering and real-time rendering. And so he was another one of the driving forces behind this project, behind both these projects. And so these projects kind of explore 2 complementary approaches to making real-time view synthesis tractable, starting from NERF-like representations. And they kind of occupy maybe different trade-offs on this quality versus speed spectrum. So ZipNerf, you can think of it as maybe like our upper limit for quality right now, and hopefully a lower bound for speed, right? Because it takes so long to render. And so the first real-time project that I want to talk about is MRF, and that's going to ask, okay, how fast can you get while you try to do the best you can to preserve the quality that volume rendering is going to give you? So you're still trying to preserve like the volumetric nature of the underlying NERF as much as possible, but you want to see how fast you can get. And then the second project, oh, yeah, that was MRF. And the second project is baked SDF. And that starts from the point of view that, okay, we know meshes are a really ultimate fast and portable geometry representation, but prior ways to try to convert NERFs into meshes have suffered from various kind of quality drawbacks. And so, and then also from the quality of the underlying mesh. So how good can we make a mesh look such that it still supports pretty good real-time rendering of these NERF scenes? I just want to quickly check, how am I doing on time? What's the, okay. Cool, yeah, let's get through this quickly. Yeah, so MRF builds on this previous work from our group, which bakes a trained NERF, so a trained volumetric NERF into sparse voxel grid style representation. And then when I say baking, I mean like you take a compute-intensive 3D scene representation, like a NERF, and you just pre-compute its outputs on a dense grid and store those in some form of memory. And so you get much faster access at render time. And so the idea of like a sparse grid is instead of tabulating all the output color and densities in the NERF on a dense grid, you can use like this block sparse representation where you chunk up space into larger blocks, completely discard the ones that are empty, and then densely store the 3D color and opacity of the others in a 3D texture memory. And so this is pretty amenable to fast rendering compared to the original NERF, because after a texture lookup, it just requires minimal extra compute that you can do in a shader, as opposed to a huge neural network evaluation. But it turns out like this kind of block sparse structure isn't really enough compression for these large real scenes that we're just looking at. So what happens here? So if you make out like a pretty low resolution, like a 512 cubed result, quality is going to take a big hit, but you have a small representation. And if you want really high quality with this, just using the SNERG block sparse style representation, you're already over 2 gigs of VRAM, right? So that's a lot for small devices. And so what we're doing here is like a more improved memory efficient representation that can scale up with a nicer resolution versus memory trade-off compared to this older block sparse style representations. And then if you're running on a beefy GPU, you can render easily real-time frame rates, like easily exceeding 60 FPS. I'm not going to get into it too much, but the representation we use is like this nice combination of a block sparse grid as before, plus a high resolution triplane representation. So we found that there's like this kind of complementary strengths to these two representations. So the sparse grid is really nice for indicating areas of free space. And then the triplane representation is really nice for kind of allocating higher texture resolution with a low amount of memory required. And so both these components end up being really important. So here's an example showing what happens if you remove the low resolution feature grid and only represent with these like triplane feature planes. And you can observe these rendering artifacts and like kind of missing texture holes in the ground. Yeah, and so here's a couple more examples of scenes in real-time viewer on this is a single customer grade GPU. And we even have demos for real-time rendering in the browser on low power devices like phones. Let me quickly get into the second real-time rendering paper we worked on called baked SDF. Okay, so there's a really simple pipeline idea for taking a NERF and converting it into a really high quality mesh. And the main thing is that actually changing the formulation of NERF to not do the standard NERF volume density and volume rendering, but use more like a vol SDF. So it's like a density that's a function of assigned distance based on this vol SDF paper. And if you kind of combine the tricks from MIP NERF 360, which I talked about before, with the vol SDF style representation, you actually end up with a volumetric representation that's really amenable for surface extraction. So you can bake a high resolution triangle mesh out of it. And then you just add, like, sprinkle a pretty simple view-dependent appearance model on top of that, which we use. Then we model the spherical Gaussians at mesh vertices. And you can essentially train a NERF-like volumetric representation, which can be triangulated into really pretty high-quality triangle meshes. And they support real-time rendering on commodity devices, right? So here, like, we're being capped by the maximum frame rate of the display, right? It's more than 60 FPS. Yeah, so it's kind of a simple, efficient appearance model that decomposes the view-dependent color into diffuse and specular color, where specular is represented by a sum of spherical Gaussian lobes. And with this combination of like MIPNO 360 and Follow CF, you get these really nice behaved meshes, and you can support like all the stuff you want to do with meshes, like maybe some light transport simulation, messing around with appearance and textures. Cool. I think, yeah, I probably don't have time to get into the next section, but thanks.
So let's thank our speaker. We are running quite a bit late, so we'll skip the Q&A for this session, but we can use the online chat for this session for Q&A. Now we have the break time, and we will get back at 11. And in the meantime, you can check out the posters. I think it's.
Okay, good. Now everybody can hear me.
Yeah, so whenever you're ready, you can unmute and start.
Okay. Hello, hello.
Yeah.
Oh, sorry. Oh, yes. You know what? I have to figure out. I'm gonna figure out. Excuse me. Shoot.
Cool. Welcome everyone to the second part of the workshop after the break. Now we have a really exciting talk by Anju. Anju is a professor at UC Berkeley. She leads the Kanazawa AI Research Lab under Bear, if I pronounced it right. Anju's research is focused on building systems that can capture, perceive, and understand the complex ways that people and animals interact dynamically with the 3D world, and can be used as information to correctly identify the content of 2D photos and video portraying scenes. I think some of the most exciting papers in recent years around this area has come out from Anju, and I'm super excited to welcome her and looking forward to the talk.
Thank you. Thanks for the kind introduction. Okay, all right, let's get started. So today is about capturing and interacting with the 3D world. So I don't really need to start in this workshop venue about, oh, here we go, about nerfs. Oh, well, let me just start with this vision. You know, we've always, do you know which movie this is from? Have you read the book? The book is actually really interesting, Ready Player One, and actually really talks a lot about this capturing a memory and going back to your own, childhood and stuff like this. And I'm like, what kind of capturing mechanism could you actually have done that? But maybe you'll do it from images. But this is Ready Player One, and this idea of going to this virtual space that you've captured, which has been visited over and over again. Like if you're a Star Trek fan, this is holodeck, and if you're a Harry Potter fan, there is Pensieve, where you take your memory and you fly through this. And then, really with all the advancements of NERF, which I don't really have to talk about in this workshop, we're getting there. So today, if you want to visit SF virtually, there is this project that reconstructed San Francisco from a virtual view. It's not on VR headset yet, but as you heard from Pratul, it's going to be soon. And then, it's getting faster and we can do all these different appearance stuff. It's getting much, much faster to train and test at the same time. And all of these exciting works that combine NERFs with generative models and all of these explosions happening. Maybe it's really interesting to solve this timeline. Okay, show this timeline. Okay, timeline, the end is off because right now we're like June, but like, okay, 3 months. Okay, so March 2020 is when NERF paper came on arXiv originally. And a year later, we worked on real-time rendering with Phylogteries and then Snurgle and the Pratul just talked about. And then also fast training came a year after that. And so we've been getting this really rapid progress. And then Block NERF was put on arXiv around this time. And around this time, we were like, maybe this is really practical and you can use it. But by this time, you can, just really forget a lot of the timeline. But by middle of spring last year, I couldn't really NERF my own videos. I would capture it and I send it to my students, and the student have to pre-process it in a very painstaking way that I couldn't really ask them to do it. And then after you get it, it takes, it's difficult to render and all of these things. And Instant NGP was a real inspiration, but then it's all in CUDA, so it's very hard to modify. So this is what really got us to thinking about writing our own open source project called NERF Studio. Here's a cool animation that somebody made for us. Actually in that timeline, Luma was also just starting. So, things are changing so quickly in this landscape. So the goal of NERF Studio was to take an end-to-end approach so you can take your phone or video or actually like things like reality capture or traditional structure for motion pipeline, and then implement NERF in a very modular way with a really nice web viewer where you can easily explore your scene, because it's very important for visual debugging, and the various approach to export. So this is like the end-to-end framework. And here's some examples. So you can actually explore the scene, and then you can look at the videos or like trajectories of the captured scenes, see how far away you are and things like this. You can render a video, and this is what the underlying video would look like. Okay, and I just want to quickly go over the ideas of NERF Studio. The design goal was to make it easy to use, develop, and learn. And I think for the interest of this community, I feel like, this is kind of more obvious if you think about it, or if you're working in NERF stuff, but actually it helped us to really talk about NERF in my lab. So after really working on NERF Studio, we really think of NERFs as 3 sets of parts. One is sampling, one is fields and encoders, and one is volumetric rendering. And sampling is really important. I mean, like much of the talk, Pratul is talking about this aliasing, and that really happens a lot. So it's really also key to faster rendering and quality. Of course, there's lots of different types of fields that you can implement, like voxels or NLP or hash encoding. And so forth, and then you can render these in many different ways. But like separating it and thinking about it like this really helps you accelerate, discuss about NERFs. The original NERF was 5-dimensional inputs into a neural network to RGB sigma, but it got more complicated and advanced, and now it's faster and better. So we have this NERFacta, which is a basic line. Basic version of it, which is that first of all, you need an appearance embedding, which describes all the different exposures. And then you have an instant NGP like small NERF field that actually acts as the color. But then you use this idea from MIP-NERF 360 that uses proposal sampler to suggest the points. And then you also use the scene contraction to capture the background. And then you also optimize the cameras. And all of the stuff that's implemented have different colors that come from different papers. And these are all implemented in a modular way, so you can actually easily combine these things. And there's lots of great documentations on these topics for you to learn. The Discord is quite active, so you could join. And then there's all these approaches where you can extract the geometry. You can also create these cool Ken Burns like camera effects. This is captured by my student Ethan, who went to Egypt after going to ECCB. So we continuously update these features. Now you can use these reality capture or OpenSFM, which is a very popular pipeline, and so forth. It's also there's also Colab. And here are some pictures, pretty pictures that are captured by our team and also people on the internet. Maybe this one I like a lot. This one's actually supposed to come with the sound that came with it. They made like a bird flying through, and then that really adds to the realism of the sound is a really important aspect that actually we need to explore in this area. Snow is also interesting. People are using it for various types of products. The really nice thing about this is that it's an open source project. Everybody's welcome to contribute. And there's this one random undergrad who was at Berkeley who's really into VFX, and he single-handedly implemented Blender integration so that you can do these super cool effects. And how this is being done is that you just capture 2 different NERF scenes, and then you render them from the same camera trajectory, which is easy in NERF Studio. And then Cyrus imported that this changed the setting so that you can import this exact same camera trajectory into Blender. You render this in Blender, and then now all you do is use your favorite After Effects or some kind of compositing software to put them together. So that's how you can get these cool VFX effects. This is our lab. And so you can do all of these things. People have used this feature to capture, export it into point clouds and do like super cool visualizations and stuff. So that's NERF Studio. And if NERF Studio is too much infrastructure for you because you're a grad student and you already have your own NERF Studio, NERF code, and you don't want to move to this whole other thing, I highly recommend you check out NERFac, which is a NERF acceleration toolbox, which is also used in NERF Studio. This was developed by Relong and my group. And we recently made an update in March, so it has changed from October. And what we did was that we made some sampling changes, taking lots of inspiration from Instant NGP and also proposal networks. And we just took these papers, their own code base, and then replaced the rendering mechanism of the sampling with NERFac, with pip install. And then just doing that with 100 lines of code change, it made the approaches like 17 to 5 times faster. So if you have a code base, I recommend you try this out. And then Rihong also wrote a nice documentation about how he goes about making GPU acceleration better. So it might be something if you're a PhD student, you'd be interested in. There is one latest update that we just actually shipped into NERF Studio, which is that NERF Studio, we tried NERF Studio Big. Okay, this is led by Justin and also other community members who were like exploring this after ZipNerf came out. And basically what we did was just make the parameters bigger, following ZipNerf. And it's similar to ZipNerf, and we're not actually implementing any of the anti-aliasing losses right now. We'd like to, but basically we're super sampling, just sample a lot. Okay, and so for the right is nerf factor big, and the left is nerf factor. And you can see that read the words so much more clearer, and yeah, really simply scaling up really went a long way. And then, this is all, the configurations is all like online now, so you can really try it out on your own system. So that's really exciting. Yeah, okay. So with that ado, okay. I wanted today talk about some research into, now that we can actually capture these things in a nice, quick way, what are we going to do with it and how are we going to interact with it? And so for the same thing, yeah, you would actually want to be able to search around the scene and query objects and fly through it. I mean, really without the semantics, NERF is really a soup of pixels. It's very similar to images. Like images have a lot of information, but images alone, RGB colors alone don't mean anything, and you really need to put semantics on there. So this is like a project that goes in this direction. So you can do like search the Waldo. You can also read text. This is a project led by Justin and Changmin, collaboration with Ken Goldberg's students. And so, yeah, so here's the idea. You look at this scene, it's a ramen. Obviously, for us, it's an egg, but for NERF, it's some kind of hex-colored particles. And so really, yes, the NERF is really, a soup of colorful particles without any specific meaning as is. And so we really want to incorporate some semantics into NERF. And we do that by taking a clip, embedding, and then incorporating into NERF. And it really allows various types of query because it's directly clip. And so therefore it preserves this open vocabulary thing. We'll get to it later. But it can actually capture these long tail objects, like Waldo. It can also do multi-scale semantics, so like utensils, all of the utensils, but a specific wooden spoon is that specific wooden spoon. And these kind of, it's really, I have multi-scale nature. Of course, it can do like yellow, all these things, and abstract query is like electricity. What does electricity mean? Or where is it? And so that's really cool. And of course, it can read text. Now, I'll explain why, because in the NERF reconstruction, the text is not as sharp, but during the training, you can actually read the text. So this is how it works. So there have been a couple of other exciting works that incorporate language in 3D. I think Andrea, who's going to come next, will, I think, also talk about this. But what is the really difference? Okay, in big words, the difference is scale and clip. Okay, so these approaches use LSEG distilled into NERF, DEDIC, or all these mask former, and all of these are fine-tuned open vocabulary detectors. If you're not aware, open vocabulary is called open vocabulary because now you're not using the fixed amount of labels, okay? But often, in order to achieve open vocabulary, you're going to fine-tune your clip into your data sets, which has specific sets of segmentation labels. And when you do this, it forgets a lot of things. So you got to be really careful when people say open vocabulary, because it is open vocabulary. Now you can call it soap bottle or dish bottle. You have to call it like a specific type of, or soap bottle only or something like this. And it works for bottles, okay? But then when you say soap, it's not exactly really, because it forgets all of these things. If you say electricity is going to so Flip knows a lot about this, but once you fine tune it, it forgets a lot of these concepts. Of course, it doesn't know about Waldo. Once you fine tune it on the data set. Yeah, so the reason why this happened is like you train clip on all of the internet, but now you're going to fine tune your clip onto your specific segmentation data set. And then it's going to forget, even with distillation, all the other things. And this is also well known that authors write about. So basically, really, the goal is how can we actually just directly use clip and encode it into NERF so that you can actually not forget all of the things that clip knows. And that's really our goal. And one thing you can say is that, okay, well, just add another head for clip. Like, why can't you do that? And really, the challenge is that unlike other modalities like depth camera or dyno features, the difference with the clip is that clip, instead of being a per pixel output like dyno or other modalities, clip is a single vector out of a whole image. Okay, so this is why it's not immediately obvious how to use clip and distill it into NeRF because there's no per pixel color, no per pixel clip. And so how do we go around this? The way we go around this is by computing clip at multiple different crops, okay? And then doing this at multiple scales. The scale is really important because at that scale of crop, that's definitely Waldo. But then at that scale, or the bigger scale, that's Twizzlers. Okay, and so same point can have multiple meanings based on its context and the scale. And so basically what you do is extract the clip at multiple scales of hierarchy of pyramid, like so. And then you're gonna make this clip hierarchy. And then at test time, when you actually, or when you train them and be like, I mean, like that particular point of that small size, then you can actually query that point in this pyramid. And if it's bigger, then you'll query a coarser level. Okay, and then so basically what you do is when you're training NeRF, now you're going to have a 3D query that you're usually going to train with your color and density stuff. And then at this point, you're also going to render clip features. The key is that you're going to actually query with the bounding box size in 3D. Size needs to be defined in 3D because in 2D things look different as you move it back and forth on the camera. So what you're going to do is pick random scale and then take that bounding box, project it into the image, and then find the closest clip features in the pyramid by interpolating. And then you're going to use that to train it. And this is a separate head, like all the other papers. You're not updating the original NeRF density and such. Okay, so that's basically how you train it. And the language loss is really just reconstructing the clip features after doing volumetric rendering in the correct feature pyramid according to that scale. So once you train this, then at test time, how you're gonna actually ask for things like NeRF gun, and then you're gonna have to, you can actually query for NeRF gun on multiple scales. And so what we do in practice, I think we can get like 15 scales query time, and you just take the maximum scale, take the scale with the strongest activation or relevancy map. Okay, so with NeRF Studio is really nice because a couple of days before the deadline, this was working, and the students went and all like took pictures, videos of this stuff. Went to the bookstore. That donut is like a donut that I usually get before the deadline, and I just captured it, and so we could use it. And then so here are some results. And I have lots and lots of results, but like, yeah, the thing to notice is that you can really do these open vocabulary searches some of this stuff. I like that. I like the bookstore because bookstore really highlights the kind of the things that you can read on it. So for example, Marie Kondo, the fun, you can actually search for it. Different hierarchies and so that is the this is really doing a textual thing. And you can imagine like if you've actually captured like a whole grocery store or something, and now you have this is a mixed reality workshop, so you can wear your headset and be like, where is the cereal that you're going for? You can do this kind of search because the search is happening in 3D. For efficiency reasons, we actually render and then do the search, but then you could be doing this in 3D and would actually use these things for the robots to go and then explore and such. And now this is implemented in NeRF Studio. So it has a really nice feature where you now have this like keyword, and you can just like type it, and it will show you the kind of relevancy map as we can interpolate it. And we use this a lot in our debugging to make sure that this is working, and this was a really nice feature. Here's more example in which that's the video that we made on the top right. You can do the same thing here, and then move around it. In a more powerful GPU, you have like as you move around, it can also look better and everything. Okay. So yeah, you can try this now. It's quite easy to. It's pip installable. Yes, that's my students are really into it. Okay, so let's compare this. So the biggest, most important comparison is comparing with the 2D clip. Okay, so you take this picture and then we ask for Lily, and then we do like many like take lots of patches and do like a scanning window for this lily with the 2D clip, and we're showing the visualization. We do this over multiple scales too, like 19 or something like this, to be fair. And then we take the highest activation at that particular point and then do that. Okay, then you can see that the clip is actually not really grounded, right? Because it's trained only with language and images, so it doesn't actually have a specific grounding. So you can't find the lily, but you can see that it's like really blurry. The thing is, once you distill it into 3D, because you're seeing this lily, similar response like this from multiple different viewpoints, and then you're also having this foreground separation automatically coming from the density, it gets really sharper, which is a really nice aspect that, like, you know, something that exists in 2D, just distilling in 3D gives you much better overlay. And here's another ablation where you do need to do multiple scales, otherwise the LERF gets confused as to what, you know, features to store at that point, because, you know, a single point can mean multiple different things because of the context. And another really cute application is that you can actually take this query, and then, you know, it gives you the maximum scale, right? Like you ask for bouquet, it gives you some, it has some maximum scale bounding box. And you can actually use that bounding box size to crop the theme. And then automatically we see that it's actually cropping out the objects that you want, because if you say you clip this, the scale would be small, and then when you crop it, Inner Studio has this nice crop feature. You can just crop out all of these different things. Of course, it's not perfect. Like one nice thing is that this is actually physically meaningful scale, in the sense that you know, this is actually happening in the 3D world scale. Of course, it's not perfect because there's more things. So you can actually say vase, which incorporates this table, but you can also subtract the table bounding box and stuff like this. And I can talk about the limitations later too, because there are more. We also do supervise this network with Dino, which was important because Dino knows what are the objects foreground and background is. That helped the, you know, this is not a segmentation mask yet. It's actually, there's like a pros and cons of keeping it in a heat map instead of a segmentation mask. You know, but Dino makes it a lot more sharper around the edges. It's, you know, there's a convergence. It's actually is not crazy slow. Here is some comparison with the distilled feature fields, which uses LSEG. And so for things that are in the distribution of cocoa objects like glass of water, it works. But for egg, it doesn't, it completely forgot what eggs are. And so we can do lots of different other comparisons, but really there's lots of interesting limitations. Well, first of all, is like, you know, this is understandable. Like zucchini looks like cucumber and corn. Okay, so there's lots of misfiring. That particular chair looks like leaf. Okay. This is a cute or important one, because Clip does not have very good grounding. Clip thinks table is these edges of the table, because whenever there's table in the scene, there's all these edges. It does not really realize that the inside, all of it is table. Clip is also bag of words. So if you say spill, you get the spill, but if you say coffee spill, you'll get both the mug and the spill. Similarly, if you say mug handle, it just highlights both the mug and the handle. Blueberry donuts will highlight all the donuts, but if you say blueberry, it will be specifically blueberry. Of course, if you know, we inherit limitation from Clip and inherit limitation from NERF. So if you didn't actually capture well or enough observations and it has a geometry is not very good, then of course it's not going to be so great either. You need to have a good set of density there. There's also this Clip splotting, you know, it's like Splatoon. When you're playing it, you're like, you know, splat your Clip features on top of it. If you didn't really see the scene from multiple views, you're gonna splat like the entire region to mean as a blue dish soap, which is yet another thing about the capture. And maybe this is another interesting thing, is that, you know, is about limitation in prompt tuning. After working on this project, I learned to be very skeptical of these open vocabulary, like, you know, prompt-based searches, because is it really capturing that object because it is a specific type of vase, or is it because it's a vase? You know, and so you really want to be careful. Like, so, yeah, yeah. So it is sensitive to prompt tuning, and so yeah, you can actually, you know, like the more and more adjectives you add, the more specifics that you want it to be. And like, this is not in itself a problem. Like humans can actually say this, but like, you know, it's not ideal if you have like a robot or like some kind of agent that wants to help you and is looking for a coffee bag, but then you have to say a specific Pete's coffee in order for it to show up or something like this. And that's not really good, right? So there's actually a lot more to study here. Yeah, but that's LERF for language embedded radiance fields. And there's other types of interaction that I'm not going to get into in this talk, but this is another one where we're using language to edit the 3D fields. And so that's, the language is a really nice interface in order to interact with these scenes. I think it's not the only one, especially when it comes to motion, but it's certainly a good multimodal signal. And so this is something that we're exploring. And it's a really nice way to interact with the 3D world that was not possible in original, like old school 3D modeling approaches. And so I think it's kind of opens up the world as to what you can do with these scenes beyond just simple editing, more contextual editing, or more queries or interaction. And we're trying to do a follow-up that uses LERF for robots to grasp things at specific locations and stuff like this. It would be really cool to also like render camera trajectories based on language, like fly around the world in a dramatic way or something like this. That would be super cool. Anyway, all of the code is out, so please play around with it. And before I end, I would like to, I'm gonna come back to this one also, but I'd like to thank my students and collaborators. So Nerf Studio is going to be presented at SIGGRAPH actually this summer. It was led by Matt and Ethan and Yvonne, and they did a really great job, followed by PhD students, Rilong, Brent, and Justin, and a bunch of master's students and undergrad students that I can't list on this on slide. LERF was led by Justin and Changmin with Ken, and then Nerf was with Ayan. So yeah, with that, I think I have a few quick minutes for questions. Thanks.
We have some time for questions, so if please come over to the mic. In the meantime, like I know you put out the limitations of the current approach. Like besides those, what are some of the next challenges of like combining language and vision? That's
I think the hierarchy is really interesting, and the grouping nature of it is interesting. I think like Nerf gives you a lot of information. It's much easier to group things in Nerfland because you already have the foreground background separation given to you with the 3D. But then that, of course, is not enough to do grouping. You need semantics to do grouping. And now that we actually have a way to incorporate the grouping, how can you actually group things with different hierarchies? I think that's actually like an interesting question, because really what makes LERF, like what's really is different from LERF is this multi-scale aspect. And I think there's actually a lot to deepen there. So that's really what I'm thinking about next. And like interaction, obviously, once the object is segmented, you really want to be able to like move things around. Like right now, we added meaning to Nerf, but then it's still like a particle that is like stuck to each other. You know what I mean? What if you just wanted to move that particular mug and stuff like that?
Thank you for your presentations. It's some work. I was wondering if you've thought about implementing some of this in video game engines, or as you said right now, like for interaction with objects. Have you done something like that, or thought about?
Yeah.
More than the VFX and stuff, like for video games and gameplay.
So this is whenever I talk to industry people, they always say it's like Nerf is great, but then like we like meshes, like how can we get the meshes? And I think that's still going to be true. Like for the next 5 years, that's how de facto like how the transition is going to go. You Nerf and then you convert it to meshes. And I think that's already the clear answer, because it's just so much faster than existing photogrammetry. And then given the progress of the situation, right? Like, how fast things move in this area, like in a couple of months, there's going to be really good mesh extraction algorithm. Maybe the Pratul one is already that. And then you can always do it. But I think this is why the instruct nerf to nerf or like LERF is an interesting example because it actually inspires, I think, new ways of interacting with objects. It's not just 3D editing, changing the color or the texture of the things, but more contextual. Actually, you can also change the geometry too, which would take a long time for these traditional things to do. So I think while this making into a mesh and then traditional transition will happen, hopefully there's also a direction that explores directly using nerfs in these applications. And there's a lot of startups that are using Nerf Studio. There's one that actually uses it into Unreal Engine and so forth. So you could do that, and then you could give us a PR request. Thank you.
Let's thank our speaker. Thanks a lot for the background.
Thank you.
Okay, can you hear me? Maybe, maybe not.
I can hear you.
And you can see my screen share.
Yes.
Okay, great. Okay. Ready when your guys are.
Can you hear us?
Yes.
Okay, great. Awesome. Let me. Okay, so let me introduce our next speaker, Andrea Bedaldi. He's a professor of computer vision and machine learning at the University of Oxford. He's a co-lead of the VGG group, and he's also a research scientist at Meta AI Research. Andrea's main research focus has been in unsupervised learning of representations and geometry in computer vision, and he has authored more than 180 peer-reviewed papers in top-tier conferences. I'm really excited to have Andrea present his recent work to us. Andrea, go ahead.
Okay, thank you very much. So yeah, I would like to talk to you about our progress in learning 3D geometry from fusion to generation. So we'll see what that means. So the starting point is an object, and we want to have a representation for it, so we can do stuff with it in algorithm, in software. So to do that, we're going to introduce a density function, which is just a function of a three-dimensional point x, and that density is going to tell us whether that point is occupied or not, whether the object is present at that location. But of course, you also want to be able to generate an image of that object. So for that, I need to know the appearance. So I'm going to introduce a second function, which is a radiance of that point, which is a function of space, x, as well as the viewing direction. And that's going to tell me the color that I can gonna see when I look at that point from that particular direction. Now, of course, this is just a radiance field. And the intuition here is that you can use a neural network like an MLP as a very efficient and effective representation of this pair of function, the density and the radiance. Of course, this is something that we have seen to death today, so I don't need to discuss it further, but that's going to be the basis of our models going forward. And of course, now the object has been reduced to just the parameters of this neural network, for example, the MLP. So the object effectively now is just theta, the parameters. Now, I also have a way of taking that function, that MLP, and render it in a differentiable manner onto an image. So for that, I only need to specify the viewpoint. And there's a process which essentially amounts to casting a ray from the viewpoint or the camera into the object in such a way that you can determine the color of that pixel and therefore render your image. You're going to repeat that for every pixel in the image. Okay, so the details are not so important, but the important thing is that there is a differentiable relationship between the object and the image I generate. In order to reconstruct an object, what I do is just simply take a certain number of images for which I know the viewpoint. I render those images based on the current version of the model parameters. I compare the results to the images I have as input. And then I try to minimize the reconstruction loss, which is just the Del2 loss between what I render and what I know those images should look like. And by doing that, you learn the parameter theta of the model, and here's your reconstruction. Okay, so this is very basic, but effectively you can also look at this process as fusing two-dimensional information. Okay, so what this means is that we have a lot of 2D images, for example, images of the Lego sequence here. or frames of Lego sequence. And through this process of learning, of determining the parameters of the model, you're going to come up with a single three-dimensional model or MLP that summarizes that information in a very compact form, in a way which is also consistent from a three-dimensional perspective. Okay. Now we have fused RGB information. So the question is, what else can you fuse? Is there something else you can do with this? Well, of course, you can fuse any type of information which is represented as an image. For example, I can take an image I, and I can apply any 2D network that produces a interpretation of the image, which can be represented as an image in its own right, for example, segmentation mask or map, and then I can fuse that, all right? So here, what it means is I'm going to take my input image, I'm going to apply an existing two-dimensional network, for example, segmentation network, something that can determine the nature of the object I'm looking at, or maybe the nature of the material I'm looking at. And I'm going to repeat this, I'm going to apply this network to all the views I have as input. And then I'm going to learn NeRF as before, but in addition to the density function and the radiance function, I'm also going to learn a three-dimensional feature function, which is going to essentially distill or summarize all the features that they extract from the individual frames or images into a single three-dimensional model. So now essentially I have featurized or added features to my 3D model. Now, one early version of this was semantic NeRF. This is maybe the most obvious way of doing it, which is to say you take a video and you apply a semantic segmentation network to individual frames, you summarize them in 3D, and now you have effectively what is a 3D segmentation of your environment or your reconstruction. But you do not need to use a supervised feature for this. You can also use unsupervised features. For example, here is the same process applied to Dino features or Dino features. This Dino is a unsupervised feature extractor that is learned from very large quantities of data, but without human-provided labels, okay? Doesn't matter. These features in 2D, they tend to correlate very well with the presence of certain object in the image. Now you can take the frames in this video, apply Dino to each frame individually, and then you can summarize or compress the information that you get like this into a single 3D reconstruction, which is now augmented with Dino features. And once you have done that, your 3D reconstruction becomes smarter. For example, you can click on a point in your volume or your image, and then you can grab the corresponding object, in this instance, the flower, automatically. And this works without any supervision, because the features you have fused, they are unsupervised, okay? But we can go beyond that. So here's in contrastive lift, what we're doing is we're taking in the middle here, you can see a per frame instance segmentation that has been obtained by using an off-the-shelf instance segmentation model. And to the right, we're fusing this information into a single NeRF-like reconstruction. And so one thing that you'll notice is that the segments here are not temporally consistent because they're extracted on a per frame basis. So there is no relationship between them. But by fusing them into a single 3D reconstruction, we can resolve this ambiguity and make all these instances consistent over time, as well as projecting the instances into this space. So now we can grab the objects if you like. But this can go on. I can fuse a lot more. As long as I have something that operates in 2D, very often I can fuse the corresponding information in 3D. I mean, I'm just shown how to do that for Clip. You can also do that for a 2D generator. So we live now in an age where we can type a textual prompt like this into Stable Diffusion, Tiki Bar in Vancouver, and after a few seconds, we get the corresponding image out. So these are very large scale models. Some people call them foundational model. They can understand a bit of pretty much arbitrary content that you can specify in text and produce a corresponding image. Now, I need to explain briefly how this works because I'm going to use that later in the talk. So the way the feature model works, and probably you're very familiar with it, is that you take a clean image here to the right, I, and then you progressively add increasing amount of noise to that, to the point that to the left here, what you get is pure Gaussian noise. Okay, that's how you generate your, if you like, your training data for the model. Now, test time, you want to draw a sample for the model from your model. What you're going to do is you're going to draw a Gaussian sample here to the left, and then you're going to go from the left back to the right till you get a sharp image by iterated application of a neural network D, which is a denoiser model. Okay, that takes the noisy image as input, denoises it progressively more and more, iteration after iteration, until you get with a sharp image back. And this is how you sample the model you have trained. Okay, that's in a nutshell how a diffusion model works. Now, once you have trained this network, this denoiser model, you can do many interesting things with it. So one thing you can do is you can use it as a sort of critic or proofreader. So what this means is you can start with a very low quality image here. For example, say a low resolution image. You can apply a little bit of noise to that. So you get a noisy version of that poor quality image. And then you can apply your denoiser to try to reconstruct a high quality version of the image you started from. So this is in a certain sense, is the proofread version of your input or an improved version of your input. So what's going on underneath is that you start with a sharp but low quality image I-hat. By adding noise, you project it into a space of images which are more, in a certain sense, more compact, or the distribution of those images is more smooth because these are noisy images. And then with your denoiser, you project that back into a sharper version of the same, which is going to be maybe as sharp as the image you started with, but it's going to live in a regional space which has higher likelihood. So you're clamping essentially the likelihood of the image. You're improving the likelihood of the image, so it gets better. Now I can use that for distillation in 3D. So what I do is I start from a noisy version of my 3D object, a noisy volume, noisy MLP, and generate the corresponding images from a bunch of random viewpoints. And then apply my denoiser effectively to, or proofreader if you like, to get improved versions of the individual views from which I can get some sort of virtual supervision to try to improve my 3D reconstruction, all right? Now, of course, this is the idea behind Dream Fusion and several works that came before that, but Dream Fusion has really done it very, very well for diffusion-based models. So here you can take something like the image general stable diffusion, type in a query, and instead of getting out single image, you can get out a distilled 3D model. But you can go beyond that. So here in CVPR, we introduce into Real Fusion, which does something very similar. But instead of starting from text, it starts from an actual real image. So in this case, the 2D model is used as to complement the information and come up with a full 360-degree reconstruction of an image that, of an object that for which we only see a viewpoint. Okay. And you can go even beyond that. So if you have a diffusion model that can generate videos, for example, like Make a Video, which is something that Meta did last year, then you can take that and distill it into little 3D animations. So here you can specify a text prompt, and through a process of distillation of a text to video model, then you can get a text to 4D model, if you like, or sampler. So something that can go from text to little 4-dimensional animations. Okay. Now this is all quite fun, so it's very interesting. So you can take one of these off-the-shelf 2D diffusion models and really squeeze a lot out of them. In terms of by this sort of test time optimization or distillation or fusion, you can extract 3D information from them in a way. Now this is nice, but of course it's also very limited. First of all, it's very, very slow to do that. So to generate an image like this, it could take dozens of minutes, maybe even hours, depending on the model, okay? So it's too slow for real-time applications. And also this model here is still 2D model, so it does not understand 3D perfectly. For example, it very often does not understand that there is a front and a back to the objects. So when you do a 3D reconstruction, you might have a character which has two faces, say. This is called the Janus problem. So what we want to do is really to go towards model that can do 3D reconstruction, or we want to do large scale or foundational models of 3D objects directly without going through 2D models first. So the most obvious idea to do that is to say, okay, so we have a model that works for 2D images. Let's just replicate that in 3D. So this would be possible, except that when you train a 2D diffusion model, you use billions of images. For example, you use Lion, which are captioned images. And that's quite easily available for when it comes to two-dimensional content. But we don't quite have comparably large and high quality data sets of 3D assets that we can use for training. So the first thing I want to discuss briefly is hollow diffusion, which is a method that can learn to diffuse 3D objects starting from 2D multi-view supervision, okay? So to explain how this works, I need, again, to review how a 2D diffusion model is trained, and then I can explain how hollow diffusion is trained. So to train a diffusion model, what you need to do, you start from a sharp 2D image from your distribution. You just sample that from the internet, say. You apply noise to that, so you get a noisy version of that. Then you have a denoiser you want to train. So the denoiser is a neural network that takes as input a noisy image and spits out effectively the denoised image. And now you can set up a loss that says my reconstruction here, my denoised image, should be as close as possible to the image I started from, the clean one, all right? Now, this is very easy to understand, and you could turn that into the 3D version of that by simply replacing images with 3D representation of objects, for example, voxel grids or MLPs. Now, this is, again, would be possible, except that we don't really have those, or at least we don't really have those in sufficient abundance. So what we do instead is, well, several changes. The first one is to replace the loss so that instead of comparing the denoised volume to the ground truth volume, I compare the denoised volume to the ground truth multiple views I have on my object, okay? And this goes through a differentiable rendering process, just like NERF does when you train it from images. But now I have a question mark here, which is actually crucial, because in order to train a diffusion model, I also need to be able to get access to the partially noised version of the object. And I cannot get that because I do not actually have the clean version of the volume to start from, all right? I just don't have it. So how can I get that? Well, the second change is to start by maximally noising that out, okay? So I'm gonna apply an amount of noise here, which is as such that this is effectively just a Gaussian sample. So I do not need to know the ground truth to get there. But this is actually, so this is possible. This is now all known, and you can implement that, but it doesn't quite work because effectively what we're trying to do here is to go from pure noise directly to a specific reconstruction of a given object, which is just too ambiguous. Now, the diffusion is iterative because you use your model ambiguity through the iterations, and here we're skipping that. So to fix that, what we do is we learn simultaneously to perform reconstruction and generation. What this means is we take our denoiser model and add to that a number of additional views of the object, which are different from the views we want to generate here or reconstruct. And we can have from 0 to n of those. And if we have more than 0, what this ends up being is effectively a reconstruction problem, not just a generation problem, which is far less ambiguous. So if you have enough views, actually, this is actually a well-posed problem effectively. And the final step is we do this here. But then once we have a pseudo clean volume, we add back the noise, just like in diffusion, we get an intermediately noised volume or reconstruction, and then we proceed with the diffusion training as usual. Now, why do we do that? Because we also need to be able to denoise partially noised volumes in such a way that at test time, we can incrementally denoise pure Gaussian noise back into our reconstructed object or generated object, if you like. When at test time, we do not actually have access to these additional training images. For this, we need training data. So a few years ago, we introduced Code3D, which is a collection of crowdsourced multiple videos, turntable-like videos of objects. Those are for 50 rigid categories in COCO. And this year in CVPR, we are introducing an extension of that, which is about pets. So these are a pseudo multi-view in the sense that the pets, they're not dead, they move during the video, but they move far less than the camera. So this is almost like multi-view supervision, although if not quite. If you're interested, there is a poster that you can check out later during the conference. Going back to us, these are examples of holo diffusion working. So here, without a test time, without any image, we start from pure noise and we diffuse a reconstruction of the object, which is of the quality you can see there. Okay, so we have succeeded in training a diffusion-based 3D generator from 2D data. Okay, so now we're here. So we have covered holo diffusion. And this is nice because we can train a diffusion model from 2D data only. But the problem is that we did acquire multi-view data. So I would like to briefly discuss another kind of approach that we have developed. So this is based on different constraints and different trade-offs. But the main change, at least for what concerns the discussion here, is that instead of using multi-view data, we use single images downloaded from the internet, but they are somewhat curated. So this works like this. So this is called Magic Pony. So we take as input a single input image. So we're just going to describe the model first and explain how this is trained. We have part of the model is a template, which has a mesh as well as a featurized version of the same. The feature is a sort of a map that helps us establishing correspondences with the images during training and during testing. And then the image is passed into an encoder network that spits out factors that explain what you see here. So the factors are photometric and geometric. So we have the albedo, the texture, we have the shape, we have the articulation. So there is a skeleton inside this mesh, which is automatically constructed, by the way, or fitted at least to the dimensional shape that expresses the articulation of the object. You have the viewpoint and you have the shading. You combine these factors together, you pass them through a differentiable renderer, and then what you get out is, of course, the image of the object. You can also get the mask, and you can get a version of those features that then we supervised by observing corresponding signal or training data. So we observe the image, the mask, as well as these features, which are again Dino features, which help us establishing correspondences. Again, during training, we train this autoencoder using a bunch of images that we get from the web. At test time, though, what we have is now that the encoder is trained. So given a single image, we're able, by applying this network, to reconstruct the shape, the appearance, and once we have that, because we also have a skeleton, we can simulate an animation of our object. Okay. Again, this is posted here at CVPR, so if you're interested, just check it out. And here are some example results of what we can get. So these are different animals. We can get a 3D shape with a skeleton. These are existing 3D, obviously, so you can rotate around them. You have a texture, and you can also deform the skeleton so you can have a little animation. Effectively, what we're doing is we're learning from static single images, little animated 3D characters, which is quite interesting, I think. Okay, now we're here. So we've done that. And this is nice, again, but there's limitations. And to me, one of the most significant limitations is that it does require data curation. Okay, so those images are from the web, but they're not completely arbitrary. They're a little bit curated, meaning we select them so they're not too noisy, they're not too occluded. So here's another idea, which is very, very recent, which I think can be quite powerful and quite general. So what you can do is, let's give up on using real data for training these models and use a 2D generator, for example, Stable Diffusion, to generate nice training data for us to train a 3D model from. Again, so we're gonna show you how to essentially do Magic Pony, but now instead of using real images, I'm going to generate them completely virtually. There is no real image involved here, using a diffusion generator. So what this means is that you can specify in our prompt, say cow, and then using diffusion, you can get a collection of cow-looking images from which you can train your 3D model. Now, this sounds crazy, but it's actually very nice because it's zero shot. Obviously, you just specify text or prompt. You rely on off-the-shelf 2D diffusion model, and you can get your training data. There is no curation involved in the sense that it turns out that this diffusion model, they tend to do noise suppression. So instead of generating a noisy version of those objects, they tend in general to generate clean versions of them. Clean enough that we don't need to do manual cleanup a posteriori to try to get data which is good enough to train our model from. This is also very, very powerful because curation is very time consuming in practice. And this can also support creativity because now you can specify whatever prompt you would like. For example, space cow, and you can get some synthetic data here to learn your 3D generator from, which is kind of interesting. But not only that, there is one more way you can use these diffusion models while training a 3D category level model like Magic Pony. And this is as follows. Again, so this is Magic Pony again. We have an input image, an encoder that gives us the three-dimensional factors, shape and photometry, geometry and photometry. Now, what I can do is I can take these factors and randomize some of them. For example, I can change the viewpoint and change the illumination. I can then render the corresponding image using differentiable rendering. And now I do not have supervision for that because I don't have an image of that object with this viewpoint and this lighting. But what I can do is I can use the STS logs, the same stuff that you use for Dream Fusion, if you like, to get a gradient that is then fed up not to improve that specific reconstruction, but to improve the model, the encoder, that is then able to perform a reconstruction of any image you see, okay? So we move the STS logs as something you do at test time into something that you do at training time instead. Okay, this is actually very useful because at test time, you still have something which is very fast. It doesn't take minutes or hours like Dream Fusion, if you like. It's still instantaneous because you have the network that does the reconstruction in a fit-forward manner. And it turns out that this way you can get something which works as well as Magic Pony, which is trained on real curated images, without curation, only without the cost of specifying a prompt. And when you test this on real images, it works just the same because the data that you generate with your 2D diffusion model is good enough or realistic enough. Okay. And now for the final part, because this is a workshop on it's supposed to be talking about mixed reality. Here's something which is more relevant to that, more directly relevant. So what we'd like to discuss briefly is the analysis of egocentric and highly dynamic data, okay, as you might get from a headset. So here's an egocentric video. This is from Epic Kitchen. If you look at it, it's pretty confusing, right? The camera viewpoint changes a lot, and you can only see a little bit of the world at any given time. So it's a lot of information, but it's hard to make sense of it. It would be much nicer if you could map that information in 3D, all right? For example, here there is a reconstructed kitchen, just a sparse point cloud for now. And you can see that the different actions in Epic Kitchen happens in different parts of the environment. For example, pick up garlic happens here, okay? That would be nice. So that's where we want to go. And to do that, we're introducing, well, last week really, a new version of Epic Kitchen, which is being augmented with 3D cameras. What we do here is take Epic Kitchen, which is a collection of kitchen-like videos, and automatically we have extracted cameras from them, which is actually quite hard, quite annoying thing to do. But once you have done it, it's very easy to do research on top of this kind of data set. Just like it is easy to do research on top of NERF, because you have these data sets where the photogrammetry, or that is to say the reconstruction of the camera, is already given to you. So now you can see here at the bottom right, the egocentric video, and then you can see the camera being reconstructed. And yeah, so we have, the reconstruction was actually very challenging to perform. So we have some tricks to actually allow things like Colmap to work on large scale and robustly on these kind of videos. We were in the end very successful, so we could reconstruct most videos in Epic Kitchen, so hundreds of them in fact. And Epic Kitchen also comes with some annotation for hands, so now you can have hands in 3D, correctly calibrated, and then you can do stuff with this data. For example, look at the case of dynamic new view synthesis, in which you can freeze the viewpoint, but still see what's happening in the video. So we have factorized away the viewpoint, but by reconstructed dynamic NERF, we can see what's happening much more clearly in a certain sense. We have 45 kitchens, we have 99 hours of videos, and we have 18 million frames, the frames with calibrated cameras now. So you can play with those things. Now, what can we do with that? So one thing you can do is, for example, looking at dynamic reconstruction using NERF. So here we have an input image to the input video to the left. After you have trained a certain special kind of dynamic NERF, which is called neural diff, it's a paper that we introduced a few years ago now. You can freeze the viewpoint, so you're not distracted by the camera motion any longer. And you can see in the long term what's actually changing in the kitchen. So for example, now there is a cartoon of milk here that wasn't there at the beginning. And because this model is layer-wise, you can even separate what's changing from what's static. So here is only, well, the idea here is that this part of the video would highlight the changes, whereas here you should be able to see everything else which is happening, including stuff which is not changing necessarily, okay? And so here's what is the truth of the state of the art in the case of reconstructing this kind of videos. So here we consider the problem of supervised dynamic segmentation. So the little benchmark we introduced with this Epic field dataset, in which we have three kinds of objects: static, semi-static, and dynamic. The static ones, just the background, never changes. Semi-static is stuff which is touched at least once during the video and moved. And dynamic is stuff which is being moved right now. We can try to do this unsupervised using either a 2D-based method or 3D-based method. So neural diff is 3D-based, is based on NERF, and MG is motion grouping, is an unsupervised 2D segmenter. And we can see that for the segmentation of static object, or semi-static object, then the 3D methods, they tend to work better. But for the purely dynamic object, for example, the arms, okay, so when they're really moving something all the times, then 2D methods are still better. Now, what this means is 3D vision has progressed by bounds and leaps, much better. It's very effective when it comes to stuff that doesn't move too much, but it's still pretty weak when it comes to modeling dynamic content. So this is where really a lot of interesting research can happen now, right? And this data makes it possible. All right, this is just saying what I just said. 3D analysis is very good for static objects as well as for objects which don't move too often, or not continuously anyway, but it's not so good for dynamic content just yet. And finally, and I promise this is the very last thing I'm going to talk about today, a replay dataset. This is another dataset we are introducing. This one is from Meta. Again, this is about looking at the problem of reconstructed dynamic scenes. So we have 68 scenes in this first version of the data. These are data scenes in apartments that they can taken from 8 static cameras and 3 egocentric cameras. Okay. They are acted by professional actors, so there's no problem with GDPR or privacy. This is all done, if you like, properly. You have 120 seconds per scene, and then you can do stuff with those. So we define a couple of benchmarks. One is new view synthesis, the new view synthesis benchmark. So as the name says, the goal here is to reconstruct objects from different viewpoints, given a subset of the video, or a subset of the camera, so maybe just a single camera, the egocentric camera. We have two versions of that. One is the fly around phase, and the other one is the acting phase. The fly around phase is like Frozen People, if you remember that paper, in which there is an egocentric operator that goes around the scene, but the actors are all trying to not move. So that's actually quite easy by comparison. And there's the acting phase, in which the actors just act. And so that's much harder to reconstruct. And this is where most of the challenges actually are. And an interesting thing about this data set is that this data is in fact multimodal. And let me see whether I can share my audio from my computer. That's gonna be hard. I don't know whether you can hear that. Okay, let me try again. Now they should be able to hear the audio.
No, she's trying to study criminology. Whoa. Yeah. But that's super different. Yeah. Oh, because she's like really, like, we're both like really into true crime, but she's like more.
Okay, so this data set has multiple cameras, as you can see, but also multiple microphones. And you can hear that they all sound different. This is the same as changing viewpoint. If you change this microphone you're using, then it's going to sound different. And for good 3D content generation, you need to be able to account for that. So what we've done, and this is posted here at CVPR, so check it out if you want, is to study this problem of new view acoustic synthesis using part of this data set. Okay. And so here you can see here the source.
You're not allowed to use your hands.
And here you can see the target audio actually recorded in the data set.
You're not allowed to use your hands.
And this is the prediction by the model. Okay, so if you're interested in this problem, which is, again, new synthesis but for audio, please check out our poster. Okay, I have there are more papers in CVPR that would be interesting for this workshop, but there's no time to discuss them. So I'm going to stop here. Just takeaways. I discussed the fusion approach, which is nice but limited, already very powerful, but too slow, and does not really learn into the proper 3D model. Then we discussed the problem of learning 3D foundational model, that the main challenge there is that you don't have enough 3D supervision to do that. And visual supervision from a 2D generator can help, though, by generating a virtual training signal, if you like. And then this problem modeling in motion, where a lot of very difficult research also is, NERF is great for static stuff, where stuff doesn't move too much. But when it comes to interpreting videos which are long with a lot of stuff happening in them, well, we don't know how to do that well yet. So I really invite you to look at our data sets and take up the challenge and try to improve reconstructions in the dynamic case. Okay, I'm gonna stop here. Sorry for being maybe a few minutes late.
Thank you, Andrea. We are running a little behind time, so we'll not take any questions, but we have a chat thread on the, if you are logged into CVPR, you can find the chat thread for stuff, and feel free to ask your questions there.
Okay, great. Thank you.
Thank our speaker. Thank you.
Bye.
So since this morning, we have learned about how to efficiently capture, how to reconstruct the surroundings and scenes and objects. Now, all of this is great, but it's not good if we can't display all of that capture and if it doesn't feel realistic. So passing the Turing test, the visual Turing test, is as important as capturing and reconstructing. And this is where our next talk is going to be focused on. And our next speaker is Rafal Mantyuk. Rafal is a professor of graphics and displays at University of Cambridge. His recent interests focus on computational displays, rendering, and imaging algorithms that adapt to human visual performance and deliver the best image quality. I'm quite familiar with Rafal's work in this area, and I can't emphasize how interesting and important it is for mixed reality. Rafal, please take it from here.
Thank you for this kind introduction. Can you hear me well?
Yes, we can hear you.
Okay, perfect. So I would like to talk about a part of a bigger 5-year project that was funded by European Research Council. And this particular part was on capturing, encoding, and reproducing reality. So what do I mean by that? As mentioned in the introduction, we wanted to pass a visual Turing test. So having a scene with a real object, we would like to capture high dynamic range light field, essentially images from multiple viewpoints with very high quality. We want to compute HDR 3D representation. It could be meshes, textures, neural radiance fields, whatever we want. But in the end, we want to show it on our ultra-realistic 3D HDR display with such quality that when people look at it, they cannot tell whether what they see is real or virtual. And as a kind of teaser, these are photographs taken from our display. So on the left and the right, you can see a pair of objects. One object in this pair is real, the other is virtual. And I hope at this point, you probably cannot tell which one is which. And obviously, looking at the photograph on the screen is not the same as seeing a tangible 3D object on our ultra-realistic display. Just to avoid confusion, just let me explain what I mean by photorealism. So in computer graphics, photorealism has been studied for many years. And today we have methods that can produce images that are essentially indistinguishable from photographs. But photograph is obviously different from a real scene. What we want to achieve is actually to go much beyond photorealism, to generate experience that would be equivalent what we can perceive in a real world. And I would argue that it's not really too far-fetched goal, because if you think what we need to deliver perceptual realism, we need high spatial resolution, temporal resolution, binocular disparity, focal depth, skew, color, gamma, dynamic range. And for all of this, we actually have technology to deliver all those qualities at the level that is beyond what our perception, our human eye can resolve. The difficulty is combining them together into a single system and obviously making it cheap, energy efficient, and small. So we are a small group, so we had to cut down on some requirements. So our display is definitely not small. It actually takes half of the room. It's not energy efficient. It actually blew fuses on a few occasions. And it's not particularly ergonomic because it's a head-mounted display, where you need to mount your head to the display, not the other way around. But one thing that we didn't compromise on is visual quality. So we did our best to deliver all the factors that were listed on the previous slide to essentially, achieve the quality that can meet the requirements for perceptual realism. So we're not the first to attempt the visual Turing test. Probably one of the first papers that I found was by Mayer et al. from Cornell University. This was the group that worked on global illumination solvers. And what they wanted to show is that the real scene box that you can see on the left is essentially imperceptibly indistinguishable from the rendering shown as CRT. But when you look at this photograph, it's certainly not the case. The image on the CRT is very far what you can see in this real scene box. And the trick was that they used this contraption, this optical apparatus that distorted both the real and the displayed scene in such a way that people really couldn't tell them apart. So it was a really big achievement, but technology was not really there to achieve perceptual realism. Much later, Bork et al., they constructed this elongated box 2 meters long with a small hole on one side through which you can look, obviously with one eye. And on the other side, you had a small scene with real objects or a display. And they showed that with a few tricks, if the scene is dim, if they introduce a bit of stray light, people really cannot tell them apart. But probably the most impressive technology, impressive project was by Masaoka et al. From 2013, where they compared a real scene with a photograph on an LCD display. And the goal was to determine what's the minimum resolution that you need so that whatever you display is indistinguishable from reality. The trick was again that the scene was almost 2 meters away from the viewer, and they used Synopter to eliminate any 3D depth cues, to essentially eliminate any parallax, any disparity. So what you saw was essentially a flat image, because obviously they didn't have a 3D display. What we wanted to do in this project is to go beyond what has been done before. So we wanted to show that we can achieve perceptual realism for 3D objects close to the observer, that are bright, and without any optical tricks. So for that, we needed not only a display, but the whole acquisition and display system. So we started with a capture of high range light field. We used just a commercial Sony A7R cameras. We also needed proxy geometry. Why? Because our representation of choice was Lumigraph. Lumigraph is quite old representation. It's not very efficient, but it's really fast and can work with 40 megapixel images. We had to align our high dynamic range light field with a mesh. For that, we used differential renderer, and obviously we had to perform all camera calibration. Then finally we had to display, and for that we had our custom HDR rendering on our multifocal with multifocal linear blending on our prototype display. And obviously a lot of work was put into calibration of the entire system. So you may ask, why do we need high dynamic range light field? Why don't we just take a pair of high dynamic range stereo images, slap it on the display, and work done? The problem is that our virtual camera, the virtual camera for a display, needs to be located exactly where the eye is. Because each user will have their eyes in a slightly different position, because the IPD is different, or maybe they put their head in the slightly different pose or location when they put their head in the display. Another thing is that, I mentioned light field, but it doesn't need to be light field. It could be any 3D representation. The point is that we need to be able to render from arbitrary viewpoint. Another thing that we need to have is high dynamic range, because our images must be precise in color and must be free of noise, blur, and saturation. And this is actually more challenging than we thought. And let me spend a bit of time kind of explaining, how much we need to pay attention to all those different details. So for example, color, I thought, this is solved problem. What a problem to actually have accurate color if we have all the instruments, if you have all high quality cameras. The problem is that the spectral sensitivity of a camera and the spectral sensitivity of the eye are very different. And what happens in the effect is that the camera and the eye map multispectral, multidimensional color signal into two different 3D color spaces. And there's no direct one-to-one bijective mapping that can map from a camera color space to the visual system space. And as an example, this is a calibration of a camera with a high quality light, standard illuminant. On the left is a target that we measured with a spectrodiometer. The right side of each patch is the result of a camera calibration, and you can see that the color is actually quite different. And this is for state-of-the-art color calibration technique. We also tried to throw at the problem neural network, but they didn't really improve the results of the existing methods. And what we found is that this is not something that can be easily solved without specialized camera. But what we could do, instead of really trying very hard to calibrate camera, we could actually optimize the light source. So this is what we did. We started to optimizing the light source for the color calibration accuracy. High dynamic range is really essential for our goal of achieving perceptual realism. Without HDR, there's no way that we could be even close to the appearance of real-world scenes. And for that, obviously, we use the decade-old technique of merging multiple exposures into a single HDR floating point photograph, which we also thought is a solved problem. But actually, it's not. What we notice is that most people use the estimator of Debevec and Malik that is really quite old, and most people use it because it was implemented in MATLAB, and people think that this must be state of the art. But if you actually start using it on a high ISO noisy images, this is not an optimal way to merge exposures. We revisited this problem and came up with very simple estimator that doesn't take any extra computation, doesn't require any camera calibration, and the results are way, way better than what a standard estimator can do. Another caveat is that exposure times that are coming from your camera are imprecise, and this imprecision could be quite high, even up to 40% for some of the cameras. I'm not sure what's the real cost of that. I suspect that mechanical shutter could be a bit inaccurate. This could be a rounding error, but also if your illumination is not perfectly static, it flickers. You can also have different effective exposure time per each exposure that you capture in your exposure stack. And why is it a problem? Because if you are merging exposure stack, you may end up with those bounding artifacts that hopefully are visible over zoom, where you can see those false contours. And I was scratching my head, well, what's going on? We are doing everything perfectly. We have really high quality equipment. Why we have those? And those were coming from those inaccurate exposure times. And the thing is that if you think about HDR merging, it's essentially a weighted average of different exposures. And this weighted average become discontinuous when one of the exposures starts to saturate. And you essentially don't have information in that image. So the obvious solution for that is to correct the exposure times. I'm not going to go over the solution for this problem. It's not really complicated, but there are quite a few caveats, and we've just submitted a paper on that. And the last thing I want to mention is that modulation transfer function really matters for ultimately, very high quality. Even if we have expensive lenses and full frame sensor, the resulting images will be soft. So as an example, this is a modulation transfer function measurement for our camera. The dots are estimated, is estimated MTF, and you can see that at Nyquist frequency, while using 80% of the contrast. And I can tell you that this is actually a very good result. Not many cameras can achieve 20% contrast at Nyquist frequency. And MTF inversion is kind of understood as a really ill-defined and really hard problem. But what we found is that if you capture very high quality HDR image with multiple exposures where you reduce your noise to almost nothing, MTF inversion is trivial. You just perform the convolution in the Fourier domain. And the biggest problem that you may have, which is boosting noise in high frequencies, disappears because there's almost no noise. You have to still be very careful, but this small trick way improve the quality of the views that you actually captured. And another thing that is also important is that MTF matters also at low frequencies. And measuring MTF at low frequencies is really hard. We even started setting everything up to perform those measurements. But then one of our postdocs came with a really brilliant idea that we don't need to do this. What we need to do is to put the camera where the eye is, display an image on our display, and then switch off the image and display the real scene with the actual object, take images of both, and then we can compare real and virtual in an image. Those two images won't be per pixel aligned, but because we are dealing with low frequencies, we don't need pixel alignment. And something as simple as histogram matching can fix most of the problems in low frequencies. Okay, so that was enough about the capture and all the tiny details that we need to care about. Let me talk now a bit about the display. So as the name suggests, the display is a combination of high dynamic range and multifocal displays. We have a relatively high dynamic range. We can achieve up to 4000 nit peak luminance. We have higher resolution of between 100 and 200 pixels per degree, depending where we put our display planes. And for comparison, like typical 4K display had about 60 pixels per visual degree. We can reproduce most of the 3D depth cues, including stereopsis and accommodation. And what's also important, our display allows direct comparison of real and virtual scenes. So we can have a real scene seen simultaneously or separately from a virtual scene. So here's another photograph of our display. Over here is a forehead rest with a chin rest, keyboard to control our experiments. And we have 4 HDR displays, the projector-based HDR displays that produce 2 different focal planes per eye. Let's take a look at the diagram of the display. So what we have over here in front of the observer, there's a box with a real scene where we can put an object for comparison. We have a beam splitters that can redirect the light path toward a pair of HDR displays. One is closer because one is at the bottom and the light path is shorter, and the other is a bit further away because the light path goes up when it's in the rays are reflected in the mirror and then goes to the upper HDR display. What we can also do, we can actually rotate by 90° our real scene box and then take high dynamic range light field of whatever scene we have inside. So we can capture the scene without really touching, without moving any objects, and go back and actually run the experiment. So the calibration, geometric calibration of the display was actually not a trivial thing, because if you think about it, we effectively have 8 displays in our system. Why 8 display? Because each HDR display consists of a LCD and DLP, and they provide dual modulation that we need for high dynamic range. So we have 4 displays per each eye. Effectively, what we had to do is to find a matrix that maps from the 3D coordinates of our real scene box into screen coordinates of every display. And we did it effectively in a similar way as we would do camera calibration. We put a camera where the eye should be. We slap a checkerboard on the real scene box. Then we show a checkerboard on each of the display captured images, and from those we could find all the transformations that we need. And we can also find the exact position of the eye because we have 2 focal planes. Why? Because you can give to the observer a simple task of looking at 2 grids shown at 2 different distances, and then the task is to move the corners of the grid to align one over the other. Once you have that, you can shoot 4 rays through every corner of the display, and you have a precise location of the nodal point of each eye. And this way we can obtain very high, very good geometric calibration of the entire system. Here's another picture of a real scene box. Over here you can see the image from a beam splitter. So this is our calibration grid shown over here. This is an eye tracking camera. We have moved this camera, but we also, another feature of the display is that we integrated an eye tracker. This is our light field capture system. This is an old photograph. So over here we have only 1D gantry. In the newest setup, our gantry is 2D, so we can move horizontally or vertically. And over here you can see a few photographs from our display. So over here we are showing that we can overlay a virtual object on top of the real object, and we are showing that we have a very good alignment of both. Geometry can be perfectly aligned. And over here you can see a virtual and real objects. And to be honest, I forgot which one is which, and I cannot really tell which one was real. Over here, the real object is on the right, and the virtual is on the left. And as you can see, we changed the depth of an object. And one on the left is blurry because it moved to the other focal planes. Essentially, we are showing that our display not only can produce a proper stereoscope use, but can also convey a correct focus cues. And obviously, what we wanted to do is to run a visual Turing test. In the experiment, we didn't actually ask which of the two objects is more real or realistic, because what is real? This is really difficult to define, and this is not a real scientific question because it relies too much on subjective opinion. Instead, what we did, we ran a free interval first choice experiment where we sequentially, one after each other, showed three presentations of the same object. Two of them were virtual, one was real, or one was real, the other was virtual. Everything was randomized. And then we ask which one of those is different. And if people cannot tell which one is different, for sure they cannot tell, which one is real. And yeah, the results of our experiments. So the performance of the participant was 44%. So they have 44% chance of actually getting it right, which is not zero. It's not perfect, but it's actually quite good. And for some observers, it is very, very much observer dependent. More experienced observers had obviously higher chance of guessing which one was different. Another interesting observation is that we actually failed to show that having two focal planes can improve quality. And the problem is with multifocal rendering. This is a really hard problem because when you try to show anything between two focal planes, whatever you present, whatever is going to be presented there is not going to be perfectly sharp. It's always going to be a bit out of focus. And this was probably the cue that let observers guess which one was faked. So the visual Turing test was not the end. Obviously, we put a lot of time and effort in building the display to create a platform for other studies. For example, in another project, we investigated how depth perception is affected by the absolute brightness of the display. And if we can model that, we actually compensated for the effect of reduced brightness. In another project, we investigated the impact of correct and simulated focus cues on perceived realism, whether we really need multifocal plane displays. Can we get away with just a stereo display? And in yet another project, we actually used the AR capability of our display because we can simulate optical see-through AR display in our setup. And then we determine how bright should a virtual object be to appear opaque in optical see-through AR. And then we created a model based on that. So essentially, this is just a beginning at a platform for running a lot of studies. Why? Because you can think of this display as a super display that can mimic other display prototypes that we could potentially build. So to summarize, reproducing reality is really hard and requires a lot of attention to details, a lot of revisiting, a lot of algorithms and problems that supposedly are solved. But it can give us insight into future of imaging, display systems, image, video, and 3D representations, and also perceptual limitations. What we can exploit in a limitational visual system to make the entire pipeline more efficient. It also provides platform for the experiments not possible before, because as mentioned, it's a super display that can mimic a range of potential displays. But it also let us experiment with the technology that could be commercially available in 5 to 10 years' time. Currently, it's not. So we can anticipate what future research challenges we're going to have. Here's the project website if you want to check more details. And if you happen to be in Cambridge, I obviously welcome you to visit my lab and see the display in person. So with that, I would like to thank you for your attention, and I'm happy to answer any questions if we have time left.
Are there any questions in the room or online on Zoom? If not, let's thank our speaker. Thanks a lot, Rafal, for the great talk.
Thank you.
So this was the last talk of the day for this workshop. I'm really grateful to all the speakers, presenters, and everyone attending.
I hope this gave a glimpse of some of the challenging problems that exist in making mixed reality work. I hope as it becomes more mainstream with mixed reality products coming into the market, like this becomes the new playground for many research problems in computer vision. So thanks a lot to everyone, and please enjoy the rest of the conference.